Morning, Ron. Morning, Dennis.
Morning. Can you hear me?
Yeah.
Okay, fine. I thought I was in the wrong. Presentation there for a second. Wrong link.
No, I just dropped in it. How's your
Is that
weekend?
Ron set up at home or what? Is that your setup at home, Ron?
What's that?
Oh, you didn't. I was seeing this pick and place machine going at it there. I don't know.
Oh, that's see the text?
I could see the text. Yeah. I can't see it anymore.
Oh, please, I have it.
There we go.
You can see the video and the text?
Yeah.
Yeah.
Okay. The text is not inverted.
No.
I'm having an audio issue. But, I'm having a hard time getting audio out of Teams. But I may have to just use a secondary device and I can pass it through.
Jeez, Ron, you had time to do all of this video editing too? Jeez, I should have given you more work on that.
record my presentation.
That would be to the copyright holder's discretion, I guess.
Okay, so I guess I am allowed to if I want to, is what you're saying?
No.
No, okay.
No, I'm saying no, that you're not the copyright holder.
Oh, okay.
Isn't everything recorded on YouTube?
It is.
Yeah.
If you want to make it simple, just video edit after if you wanted to. I don't know. Mr. Broad.
I think we should
Okay.
yeah. So if Ben, if you want to start that recording now, you can.
Okay, then.
Or I can do it if you want to.
Well, I don't think we really need to start right now because we only started 10 minutes or so.
I'm going to start talking about 4 there. Throw that there, but probably better at that point.
I just started it because I figured we'll forget if you don't start it.
Okay.
And that asks the question, who wants to tell this gospel when a potential copyright issue?
There you go. Jeez, Ben, you had to open that can of worms.
Honestly, I just kind of maybe for going to be able to look at it later, you know, maybe in a few years when I'm like, oh.
No, it's great. I'll tell you something. When I was taking the course and we were doing presentation, we videotaped. There was a video camera in the back of the class taking the videotaping, and we had to self-evaluate ourselves based on that. So once the presentations were done, we would sit there and watch ourselves, and we had our own little rubric we had to fill out. Basically, you know, I could find a variety of either shortcomings or best things you did or whatever, and I found it very enlightening because you don't notice the little mannerisms and the little, you know, well, for example, I'm a big kind of guy that I use that a lot, and you don't realize it until you're watching yourself and, wow, I see that a lot. So it was really a great way of you know, a little bit of self-perfecting. Yeah, so I've always you should be videotaping, and you guys should be actually part of your market should be a self-evaluation. You have, you know, let's say 20% of the presentation would be you determining what how you found your own presentation was, and most people are honest about that. They'll say, "Oh, I did a lot better than I thought," or "Not as great," or "Wow, I was right on the money," or whatever. You know?
See, that's what I was going to mention is maybe the honesty aspect. You know,
surprisingly,
we learn ethics. So
yeah, surprisingly, it's quite high actually. That's most people tend to be honest with themselves, and to be honest, it's kind of hard to keep in a way because you're also getting a mark from other people that are watching you. That like you said, you performed the best presentation you ever saw in your life, and you got marks of 40s and 30s with everybody else. But there's something askew there. Right? Sure. Alright, I'm enthralled in Mr. Broad's video here.
Pretty good.
Yeah.
I realized this morning as I was looking for a dress shirt that I outgrew most of my dress shirts.
Yeah, that's what you call it after a while. Outgrew.
Yeah.
Steady employment has that effect.
Yeah. I only have this one dress shirt and I just spilled coffee on it, so I guess my luck now.
Alright, so it's 8:25. I guess I'll start just the sequence of events. So welcome everybody to 2021 first
Just give me a second.
Oh, sure.
Make it live.
Oh,
Yeah. I didn't know you would do that.
oh, sorry. 8:25. So I should have. Well, I can wait till 8:30 and oh, okay. Well, there you go. I can wait till 8:30 and just we'll be 5 minutes late. That's all. Ben will make up for it.
I've got an awful lot to talk about in my presentation.
Oh,
so.
all right. I won't be long.
I look pretty excited for the presentations.
Oh yeah,
For the
yeah.
stream there.
Yeah, you're good to go. I just on the stream they're hearing music, right? So like as the video's playing, they're hearing them,
Oh, I see.
so they know that stuff's happening. So anyway, you're good to go. You can start this time.
So can they see me right now, or
I believe so.
because all we're seeing is a frozen version of your Teams window there.
Okay, hold on.
Oh, there you go.
Some movement.
The movement. That's right. All right. So actually, be good now, Ron.
Should be good to go.
Okay. So we'll try this again now. We're having a little bit of technical difficulties at the start, but that's all right. Welcome to the 2021 version of the NBCC Electrical Electronic Engineering Department's Symposium, Senior Project Symposium. We're calling it that now, since we're using a mix of technologies and delivery methods. This year, once again, we've had to deal with the issues of COVID-19 restrictions and such. So it's pretty much an online event. However, we are hoping that next year we can go back to the live version of the presentations. At which point, I think we're going to keep the online event streams going anyways, because it's we've got some great feedback from industry partners and anybody else that's been able to watch. Having said that, if you experience any technical difficulties, by all means, get a hold of us. We would really like to hear feedback on how we're doing for improvement, obviously, this year and in the future. So by all means, if you have difficulties maintaining a stream or anything like that. So today we are going to go through 6 presentations. Like I said, it's been a challenging year, and the students are really eager to show their results. And just before I start, though, I just want to point out that I have a few people I just want to thank. Students tend to thank their instructors and such, and I just want to thank a few people. I want to thank the advisors, Denis Legier, Don Parker, and Ron Broad, because without those 3 individuals, my job as the coordinating advisor, whatever you want to call it, would have been a nightmare. And they really help pick up the slack. We don't get much extra time during SPL sessions to do the administrative side of things. And without their help, I would have been definitely I would not be functionally healthy right now mentally, I think. So I just want to point that out there. Those are my thanks and my salutations and tip of the hat. Having said that, though, the stars of today's show are the students. for the next week or so, and we are. I know I am. I look forward to this every year. This is part of the end product for me. It's really interesting, and I really am eager to see what our students have to show us. And I learn from every presentation. I think everybody that watches these does learn things. So at this point, we have 20 some experts in their own little niche fields, and they're going to share their findings with us. So at this point, we will have 4 presentations this morning, just to put the schedule, following the schedule, and then a 75-minute break, I believe it is. And then we will resume at 1:30 for the final 2 in the afternoon. That'll go on for all 4 days. All right. So without any further, I'm getting some feedback from the mic there. Anyways, without any further ado, let's get the first presenter on virtual stage here. So that'll be Ben Babineau with his delay effects pedal. So there you go, Ben. Take it away.
Good morning, everyone. I just have to share my screen quickly, and then I'll get started. So my name is Ben Babineau. I am a senior student of the electronics engineering technology, the industrial pathway. Before I start my presentation, I've kind of got a little fun fact about myself. So when I was 14 or 15, I started collecting CDs, and I remember one of the first CDs that I bought was this one here, which is Pink Floyd's Dark Side of the Moon, which is a very iconic album for sure. It's the album cover. Most people have seen this one. The reason I bring up this CD specifically is because Pink Floyd uses a lot of effects in their music. So a good example of one of their songs on this album is Any Color You Like. In the beginning, the synthesizer has a delay effect, and this delay effect is characterized kind of as an echo. So my project is the delay effects pedal, and what we'll be talking about really this morning is the purpose, so what it does, how it does it. We're going to go through the block diagram. We're going to go through the schematic, the physical description, and then we're going to talk a little bit about the testing. So the purpose of the delay effects pedal, like I mentioned earlier, it adds an echo to an input audio signal. So in my case, later I'm going to be showing you the way that it interacts with the guitar, but it can be used. This effect can be used with other things. Why would you want it to do this? So the reason really is because it gives you a different tone. It gives a different kind of feel to your music. And like I said before, a good example, Any Color You Like is a great example of how you can use that effect. And it really is, it almost adds like a dreamy kind of feel to a song. So this is the block diagram. The reason I have this here is just to kind of quickly go over how everything interacts with each other. So in the top here, we have the power supply, and this starts with a wall adapter. So the wall adapter is a standard 9-volt wall adapter, plugs right into the delay effects pedal. And then we have a 5-volt regulator, which powers the echo processor here. So that'll it will power the delay chip, which I'll talk about later. Then we have a voltage divider, which enters the I think it's the non-inverting amplification, or the non-inverting input for the differential amplifier that's here. If we quickly go through the block diagram, our input signal goes into a signal buffer, and the signal buffer will send that signal into 2 different directions. We have one going into the differential amplifier here, which also acts as a summing amplifier and a filter, a low-pass filter. And the other direction goes through a switch and into the the echo processor. Whether the switch is on or off, it'll allow the signal to flow through. And then from here, the signal will go into the differential amplifier, and it will also be sent back into the echo processor, and this will create that repeating the echo. Really, we can control the amount of repeats, the time between repeats, as well as the volume of the repeating signal. And then from there, it's output into an audio amplifier. This is a schematic. So in the schematic here, it's laid out pretty much the same way as the block diagram is. We have our power supply on top, our input section here. We have our switch, our delay circuitry, and then our output circuit here. So I'm going to go through each different section, starting with the input. So our input starts at J2 here. So our input connection is a 6.35 millimeter audio connector, and this is a standard 1/4-inch jack that's used in lots of audio aspects, or lots of audio interfaces and stuff like that. Guitars use it, amplifiers, plenty of things. Then we have this capacitor here that filters out very low frequencies, or lower frequencies, as well as stops or impedes a DC component from going into the input device, which I'll explain a little bit later. This voltage follower here has a gain of 1, and so the input signal will be replicated from the input here into the other side of the voltage follower, or to the output, and then this output signal will go in 2 directions. Like I mentioned before, it'll either go down through this JFET or into our output through R4 here. This little section here is actually used as a voltage divider. This is the voltage divider that supplies our 4.5 volt, and that will go out into the differential amplifier, like I mentioned before. So for our switching mechanism here, this works using a JFET. So this is a P-channel JFET. The way a P-channel JFET works is if when the gate source voltage is 0, the channel will be open, and if it's above, or if it's above a certain threshold, the gate will close, or the internal resistance will increase until no current can really flow through. So this is actually a modification I made. The original circuit used an N-channel JFET, and during my prototype, it didn't seem to work the way it should have. So I fashioned this one instead using a P-channel, because it's easier to shut it off using a positive voltage than it is to try and turn it on using a negative voltage. So this 9-volt source, if we have it connected in series with the R24 and the LED here, our LED will turn on, and it will tell us that the effect is going to be applied. In that case as well, the gate will be grounded, so essentially 0 volts. Now, I'm going to be honest, I've been having problems with this in the final build of the delay effects pedal, and I was up probably around 11 o'clock last night, and I figured that it might have to do with this capacitor here, because of the way that it opposes change in voltage, right? So when we have our 9 volts connected to this portion here, what's supposed to happen is the positive voltage will be applied here, and since our JFET is a field effect transistor, the voltage will close the channel, the P channel. Our diode here, D2, is strictly there for current purposes, even though the 1 mega ohm resistor here doesn't allow much current to pass through anyway. But in case there was ever some sort of large surge or a large source of current flowing into the gate, this diode here will protect that. Now this is our delay circuit. In the delay circuit, I included our input section here. I included our output and the switch here. So just as a recap, we have our input circuit, or our input signal flowing this way. We have a capacitor here, also blocking out the DC component that's applied over here, which I'll explain later. And from this point, it enters into the PT2399. The PT2399 is the delay processor that that I use, or that's been chosen really for the delay circuit, because that's the sole purpose of the chip itself. Right here at this junction, it kind of looks as though the signal flows in two directions, but what actually happens is the signal converges from this direction here and the input. So on the inside of this processor at pin 16, this is the input, and there's an operational amplifier, an internal op amp here that acts as a low pass filter. So this low pass filter, the cutoff frequency is approximately 2.77 kilohertz, and that's calculated using an equation it's 1 over 2 pi times the square root of R20, R23, C16, and C15, and that comes out with our 2.77 kilohertz. Now, this is the inner modeling of the PT2399 circuit. This is from a website called electrosmash.com, and the reason that I took this model is because the PT2399 datasheet is kind of infamous for not necessarily being incredibly clear with what exactly happens. So this website here, what they did is they took a bunch of different resources from other people who have designed with the PT2399, and they put everything together, and they came out with this here, which seems to make a relatively good amount of sense. So on the inside of the PT2399, really the purpose, what it does is it converts the analog signal that's input into a digital signal. That digital signal is then stored and then reconverted into an analog signal. So we have this delay line here in this comparator. So our input, pin 16, and pin 15, here's the output of the first filter. And then the comparator output is passed through a delay line, then a modulator, and then another filter here. So what we can tell from this is that the comparator is actually comparing the input signal to a previous version of itself. And this outputs a bit stream that can then be stored in the memory of the chip and delayed and then reconverted into an analog signal that can be resent into the comparator. The delay line clock speed is controlled by a voltage controlled oscillator. And we have an op amp here. If we look at the circuit, our pin 6 is where the inverting output of the op amp is. And as you vary the resistance on pin 6, the gain of the operational amplifier will change. So if the resistance is very high, then the gain is low because of the equation the gain equation, which is in this case, I believe, this is inverting. So it's it's minus, the gain equals -1 over, or minus the R6 value over the, or in this case, it would be the internal resistance in the feedback loop times, or over the resistance of the 47 kilo ohm potentiometer and the 1 kilo ohm, or yes, 1 kilo ohm resistor in series. So after the delay, and then the after being delayed, it's stored into the memory of the chip, which is 44 kilobits of memory of RAM, and it's then output. It's reconverted into an analog signal after being delayed, and then filtered again through another low pass filter, and this filters out noise or potential noise that's created during the analog to digital conversion, and then it's output at pin 12. Now, pin 12 here actually leads into another low pass filter, and this will filter some more, and it uses it's actually the same values, if I remember correctly. No, actually, they're not the same values. My apologies. Up here, they're the same values. So the output of the operational amplifier is at the pin 14, and then from here, the signal will either be fed back into the input of the PT2399 or into the output. So depending on the resistance of the repeats potentiometer here, which is R8, which is 10K resistor, or 10K potentiometer, the amplitude of the signal will actually vary. So if the resistance is very high, then the signal cannot necessarily propagate more than once around. So our input signal will repeat one time. In the opposite sense, if the resistance value is very low, then it'll repeat as much as it can. I haven't quite figured out the amount of repetitions yet because it's very long. The volume potentiometer works the same way. If the resistance is very high, then the volume will be very low. In a perfect world, really, right now, I'm also having problems with this volume potentiometer in the final project. What should happen is the volume will decrease to 0, so you won't be able to hear it at all. And in the other case, if the resistance is very low, then it should meet the input signal strength. From here, we go into the input, or the output, sorry. From the output, like I mentioned before, this is a differential amplifier, a summing amplifier, and a filter all at the same time. So the way that these filters work really is we have our capacitor and our resistor here in parallel, and depending on the frequency, the higher the frequency of the signal, the lower the impedance, or the lower the impedance of the capacitor is, which means that as the frequency increases, the gain across the gain of the amplifier actually decreases. So in the sense, if it's a DC component that's being amplified, then the gain is 1 because of our 10K over 10K here. And in the case if the frequency is very high, then it'll be essentially a gain of zero, or yeah, I guess you could say the gain. So this 4.5 volts here, as I was explaining before, is the DC offset. The reason that we have this DC offset is because there's no negative voltage source in the circuit at all, and for the operational amplifiers to produce a negative voltage, a negative source is needed. To kind of get by this this problem, because we don't have a negative source, we can set a base DC offset of 4.5 volts, which will allow our signal to be able to fluctuate from a higher and a lower point, causing our analog signal. And this actually goes all the way back into our input. And the way this does that is that our pin 6 and our pin 5, the voltages should be the same because of a virtual ground. Because of our capacitors blocking out our DC source, our input here, or I guess really the way that this should be explained is our since there's no current flowing, the voltage is able to, or there's no current. Since there's no current flowing, the voltage kind of propagates where it wants to, I guess. So this voltage follower, since it's a gain of 1 and our input or our output has a DC offset of 4.5 volts, that means that our input also has to have a DC offset of 4.5 volts. And that's really how the DC offset works at the output. Now this is the physical construction of the delay effects pedal. We have our 3 potentiometers here. We have repeats, the volume, the delay. We have our LED here that allows the device to either be turned on or off. In this case, it's not fully functional. The LED does turn on and off, but I think that because there's a problem with the JFET circuitry, the effect doesn't necessarily turn off when you apply or when you change the switch position. Now, the test that I had, we had a delay time test, which was or I kind of forgot to mention this. We, because of COVID-19, we weren't necessarily able to do our tests in time to submit in the report and to present during the symposium. So what I'm going to do instead is kind of present my tests as they should have been and give approximate values to what the values should have been as well. So the delay time test was really just to measure the maximum and minimum delay time, which if we go from the original circuit designer, which is Merlin Blenko of Valve Wizard, his design would go from 30 milliseconds approximately for the lowest amount, or the lowest repeat time, and then the maximum was approximately 400 milliseconds. The way this would be done, or the way that this would really be measured, is we would take an oscilloscope, we'd attach it to the input, and we take another channel of the oscilloscope and connect it to the top of our circuit right here. So this is the reason I picked this spot here between R10, C9, and R11 is because our volume potentiometer here is variable. I probably could have also placed it here, but the volume potentiometer would have to be adjusted to ensure the maximum volume. Using a waveform generator, you input a pulse signal and then really measure the time between the first and second, or the input signal and the delayed signal. And then by varying the delay potentiometer here, it'll either increase or decrease. For the test of first repetition attenuation, this is really as a means to measure the input voltage compared to the output voltage of the IC. Now, in the case of the IC, it uses what's called delta sigma modulation, which is constant sampling of the input of the input signal as it converts into a digital signal that can then be delayed and stored and reconverted. So from what I've seen, I'm not exactly, I'll be honest, I'm not exactly 100% sure of the value that should be output. From what I understand, there's the chip itself is very low noise, but there's not a whole lot of explanation about what the attenuation is across the chip itself, across the input and the output. So to conclude, I've put a lot of time into this. I wish I'd have more time, really, because then I'd be able to fix the problems that I've been having. Like I mentioned before, I might have figured out some of the problems. Although that there are a lot of issues, I think that I definitely learned a lot from this. This is probably kind of the area I would like to work in as well. Audio processing is very interesting to me. Being a musician, I very much enjoy playing music and seeing what different effects can be applied to an audio signal. And that's pretty much my presentation. We're going to go to the demonstration now. So in the demonstration, quickly before, I'm just going to explain because I kind of have the time. So I'm going to play a song called Rain, which is a song by a YouTuber called, his name's Rob Scallon, and he's usually a metal guitar player, but he wrote the song, and it's very highly dependent on delay. Now, I won't really be able to show you the, I probably won't have the time really to show you the, I might have time to show the problems, but the main issue is that I won't be able to show you the song without the delay. So I'm going to play the song. After playing the song, I'm going to kind of mess around with the controls just to show what it can do. I'll also show you that it can't turn off. And we'll go from there. So I'm going to switch my camera and my microphone. Try to do this as quickly as possible here. Where is my here? Just so you know, when I switch the microphone, it'll switch to this microphone here, so I won't really be able to talk. Alrighty. Can you hear me? That concludes the demonstration. Could you hear it?
Yep.
Yes.
Okay, thank God.
Sound very good.
Yeah.
I'll
Alright.
stop sharing my screen, I guess. Oh no, wait.
Yeah.
Go here.
You can actually leave the screen share because we may have to want to refer to some of the schematics and so on, right? So.
Oh. Uh-oh. Okay.
So you might as well just. All right, leave it like that. That's fine there, or whatever. As long as we can reference some schematics and. I don't know. A very good demonstration, by the way. Very nice sounding pedal.
Thank you.
Could you just quickly go just a couple of sentences there, review what doesn't work on it? I really at the end there I just didn't catch what doesn't work.
Okay, so problems that I'm having with it right now is the power switch. When I click the power switch, the LED turns on and off, but the delay is still applied. So
Okay.
this, I'm fairly certain, is a problem with the gate to source voltage on the JFET when it switches.
All right.
Other problem I'm having is the volume potentiometer. When I turn it all the way down, the volume doesn't actually go all the way down. So it doesn't. You can still slightly hear it. It's very low, but it's not zero like I'd like it to be.
All right.
Another problem, I don't know if I actually mentioned this one, but there's a large amount of attenuation from the input to the output. I haven't been able to figure out exactly why it's caused or what's causing this. It's between maybe I'll pull up my schematic actually. So R4 here, when I was testing this, when I was able to, the output of the voltage follower was very, very, very low. Or actually, no, the output was okay, but the voltage here, voltage on this side was very low, and then that would also make the output of the.
What was the voltage at that node? You say very low. I'm just curious.
Very low. If I remember correctly, you couldn't really see it actually when we were measuring.
So
we
was
were
it
using an oscilloscope, and it was practically just noise. But if
AC
you
or
turn
DC coupling?
That would be AC coupling, I believe.
AC coupling? Well, that would be why. Because again, I'm just going to remind you a little bit on your op amp theory here. This is what kind of inverter is IC2?
IC2, that's an inverting.
Okay. So in that configuration, what can you tell me? Not looking at your circuit, but if you had an inverting amplifier like that, what can you tell me about the voltage relationship between pin 5 and pin 6?
Should be the same.
Should be the same.
Yes.
And what is pin 6?
4.5 volts of DC.
So what should be pin 5?
4.5 volts DC.
So when you looked at it in AC coupling...
See, we were using a waveform generator. That's the only problem.
Doesn't matter. That doesn't matter.
Okay.
If you're firing a signal in here at the input of R4 there, it should still an inverting op amplifier works like an inverting op amplifier. Period. Right? It follows the same. So the problem is you're trying to find voltage signals. In reality, is an op amp fundamentally works as a current device. It transfers current between its output and its input. So, yes, I'm not surprised you didn't see anything at pin 5 because the whole function of a non-inverting amplifier, okay, is the fact that it's trying to keep pin 5 and 6 at the same voltage because the current going to pin 5 and the current going into pin 6 are equal to what?
4.5 volts.
No current.
Oh, the current. Oh, would be. Can I get a calculator?
If you don't need a calculator, it's high impedance. It should be very, very, very small, right? High impedance inputs, right? To the amplifiers.
Right. Yes. From pin 5 to pin 6. Yeah.
That's right.
Yeah.
So if you don't see any difference in current there, you shouldn't see very significant difference in voltage between pin 5 and 6 either. So how does that accomplish that? It accomplishes that by syncing or sourcing current from pin 7, right, all the way around the feedback loop, back around. That's how it's maintaining those conditions, right? We can't cheat Ohm's law, right? Okay, so it does that by sending current in from that way, okay, to maintain everything as it should be, okay, and it does it much faster than you and I can look at it, and we'd be able to do it manually. And therefore, the effective result of the model that we use is that pin 5 and 6 have very little current going into it, very little voltage variations to it. Where you should have been looking at voltage variations is on the input side of R4 and on the output of the op amp. By all means, those would have been the places to look at.
Oh,
right?
okay. Because
now,
since pin 7 is giving off or sending out the current.
That's right. And R5 limits the amount of current. That's why we have negative feedback to control the whole thing, right? Because this in the end is a very high gain amplifier, right? Yeah. The other thing I want to point out is you wanted to do the second test there. I forget what you called it, but anyways, your second test is actually what you just described right there. It should have been testing the output of J3 compared to J2. Okay, that would have been a much better second test, because
instead of
and well, that would identify that your TLO72 is having issues of gain, because most music pedals, they will have a higher a positive gain at the output to make up for any internal signal drop that exists, right? There's going to be signal drop in the input through the process, so your output gain should be higher than the input, so you can make it equal, so when you kick the thing on and off, you don't hear a signal variation, right? You want to maintain the same signal. So it would have been more appropriate for you to have a output versus input gain test. And in fact, if I know you're going to do the test next week, I would amend my test to do that, because otherwise what you're actually doing, you're really only doing an internal block test, which is all right. You're going to need to do that to probably figure out your problem. Okay. But the reality is, if I was going to buy your pedal, which by the way, it sounds great, and I would be, it would be interesting to, if it was really functional, to say, hey, that's a really great little, boutique pedal to have. Yeah. I would be much more interested in the overall gain of your pedal than I am whether, TLO72 has a gain of 3 dBs or -3 or whatever it is, right? I mean, that's what it would amount to. Does anybody else, advisors, have any questions? I don't want to take up the whole time there.
You just carry on there, Dennis.
All right. Can I ask, can you go back to, you have it right there. How bright is your LED one?
I would say it's an okay brightness.
It's an okay brightness. Yeah, be more
I didn't
quantitative
measure it in
than
lumens.
that. No, but you could estimate what it is based on the current going through it.
Okay.
Right?
I think the current going through it it's like 2 milliamps. I think.
Yeah,
like
not
that.
even
it's
about
1
point. Yeah, 1 point.
Yeah.
So that's what got me. I saw that 4.7K and I said, wow, that's not a lot of current going through that LED, unless it's a super bright LED that's got some kind of weird numbers associated to it. I was like, that thing definitely not sunlight readable for sure. Okay, so again, why did you pick that 4.7K? Why not? Most LEDs are operated at 10 milliamps, something like that.
Yeah, much higher.
Yeah, if they're really too bright, then you ease back a little. But you're 1/10 of what it should be operating at, right?
This is the reason I picked this was actually because when I was in the original design, he had a 4.7K resistor in series with his LED. So because I was kind of crammed on time during the prototype build, I just used the 4.7K and I moved it over. But it's one thing that I did think about changing the value there, but what happened?
That's an easy calculation, right? And just quick substitution. I mean, I was just curious, maybe it's something about the LED one. Also, you mentioned D2 and the purpose of D2. Could you restate that purpose? I don't know if anybody else wants to talk about that there as far as instructors, but I just want to hear what you said about D2 again.
So from what I understand about D2 is that it's there really to block the current going into the gate if ever there's some sort of large amount of current, which this is also something that was in the first or the original circuit. I wasn't entirely sure the exact purpose why it was there. I just kind of figure that this is the point
Well,
of this diode here is
so-
to protect
So tell
the
me about
gate.
the gate of Q1. What do you know about the gate of Q1,
Oh.
current-wise and impedance-wise?
So gate,
That's
this,
going back
since the
a
P
year or so.
channel, I think I go. I see what you're asking here. Is that since it's NPN, since the junction is technically an NPN junction, if I remember correctly, when it comes to
Well, yeah, it's a
the
PN junction, but
yeah,
when you look into Q1, what do you expect to see impedance-wise?
from it should be very high.
Very high. That's right.
Very high.
JFETs and MOSFETs are voltage.
Control.
They're current controlled voltage devices, right? They're transconductance devices, right? Okay. So if we look at the gate Q1 versus R27, R24, would you say they're in series or parallel with those resistors? Do they qualify
They're in
as
series?
Really? They qualify as in series? R24? No way.
No, not exactly. Because
Yeah,
okay. I
more
see.
in parallel, right? So we know that
Yeah.
current and parallel branches are independent of each other. So therefore, what would be the source of your high current? If Q1 is considered to be a very high resistance, and you have R27 and R24 that are in parallel, okay, there's nothing you can do to R24 or R27 to change what's happening in the path of Q1 because they're in parallel, okay, right?
Right, yes.
So what would be the source of a high current scenario? Well, it could only be Q1 failing, right?
Okay.
So if Q1 fails, what is D2 protecting?
Nothing.
Nothing.
Nothing at all,
That's right.
because
It's not
it would
there
push the
for
current
that.
through the gate, right?
Yeah, it's not there for that, okay? That's
Okay.
basically what I'm saying. D2 is there to do biasing, and I suspect it may be a part of the problem of why your gate doesn't close off totally, and you're still getting output of the device, okay? You may want to look at what's happening there, all right?
Okay.
So I'm not saying D2 is the problem, but maybe the biasing of the JFET there is an issue here, right? It's obviously not pinching off correctly. All right, I think
Alrighty.
does anybody else have any other questions there? I think we're kind of, according to my time, we're a little over there.
Yeah, I should be all right there.
Ron, Don, you guys are good too, or?
Yep, good here. Thanks, Ben.
Thank you.
Okay,
Thanks for listening.
well, we'll stop there. Thanks, Ben, for your presentation. It was a good presentation, very informative. I hope
Awesome.
you've got a minor part not working or two, and I hope you get to work the bugs out for that, and you'll have a great pedal there.
Perfect. Thank you very much.
Right on. We're going to be taking a few minutes break here. The board, the evaluation board, is going to be filling in their evaluation sheets and such. So we'll be back at 9:30 to have our presentation with, hold on here, where's my schedule? With Mr. Shaw on his electronic mailbox. So join us at 9:30 for his presentation of the electronic mailbox. Thank you. All right, so take a small break, and we're back. Right now, we're going to listen to Mr. Umang Shaw talk about his project, which involves an electronic mailbox. And the floor is yours, Mr. Shaw. We're not hearing your microphone.
Maybe now?
Yes.
Yes.
Try it again. Yeah.
Thank you.
Please proceed.
Can you see my screen?
Yes, we can see it clearly. You can begin your presentation.
Thank you. So hello folks. Today I am here to give a presentation on my SPL project. First, I want to introduce myself. My name is Umang Shah. I am in EET department in NBCC Moncton. So before starting the presentation, I want to tell you about the situation right now. Lots of people are facing, and in the past, lots of people faced. And today in my present, I will give you some more interesting and some other facts about my presentation. So if you are waiting for an important mail and you want to get as early as possible because it's very important for you. For example, if somebody is waiting for their paycheck and because he already ran out of money and he wants to get as early as possible. So in this situation, we will visit lots of our mailbox lots of time. So here and my main focus is on mailbox. Everybody knows about the mailbox. It is situated outside of the house and it is required to receive the letter. And the mail is a part of the postal system. So the mail carrier who delivered the mail, he drops the letter in the letterbox and goes away without giving any information about the letter to the users. So users cannot know that they have mail in the mailbox. So because of this situation, every time we have to go and check our mailbox once in a while during the day. So here I found solution by making electronic mailbox. And right now in the increase of standard of living, there is a sense of urgency that would so if we use electronic mailbox, so we can solve this problem. So here so in today's presentation, I want to give some brief description about the electronic mailbox which I made for as my SPL project. So in today's presentation, I want to give some information about my project. So I will focus on 6 main topics. So the first topics is objective of project. In this part, I will tell you about what's the main purpose for making this project. And after that, I will show you my concept drawing so you can understand how actually the my electronic mailbox is looks like. Then I will tell you about the functionality of this mailbox, what's the working principle of this project. Then we will discuss about some other parts which I use and what the main part which I use for making this device. And after that, we will discuss about some drawings and diagrams which I made for my project. And in the last, why we need to make to use this device. So to find out that we will discuss about some advantages of my project. So first of all, in the objective, the main purpose behind making this project is to make a device which can tell us that you have letter in the letterbox without you can understand that there is a letter present in the mailbox without opening it, and also it tells you how many letters you have in your letterbox. You can see this the number of letters on the LCD screen. By using this device, you can save your valuable time. So here it is my concept drawing. There are total 3 main parts in my concept drawing. It's a 3D view. So the first one is front view, the other one is the side view, and on the top is the top view. So the front view is the main part of this mailbox. At the left side of the front view, I put one LCD display, and on the other side there are 2 LCD. The LED one is red and the LED 2 is green. LED 1 indicates as a power LED, and LED 2, which is the green LED, is working as a letter indicator. And about these 2 components, there is a one letter slot where someone can put letter, and inside of the front view I put IR sensor, infrared sensor, exactly near the letter slot, so it can sense the letter very easily. The length is 32 centimeter for this mailbox, and the width is 30 centimeter. In the side view, I made one door. It's 11 centimeter long. So by using this door, the user can easily take out all the letters. And at the bottom of the side view, I attached the reset button. So when the user take out all the letters, after that, when he close the door, at the same time the reset button will also press, and this reset button reset the whole circuit of this mailbox. When someone drops a letter in the letterbox, the second LED, the green LED, which is working as a letter indicator, will turn on. That indicates that you have a letter in the letterbox. And also on the LCD display, you can see the number of the total letters you have in the mailbox. And when you press the reset button, this whole circuit automatically will be reset, and the green LED will turn off, and the red one will stay on because it's a power LED for this device. So now I want to talk about the functionality of this project. The functionality of this project is very simple. the light I use means two LEDs, the red one and green one. Both are attached with Atmega microcontroller, and the IR sensor, which is also connected with Atmega microcontroller. IR sensor is first of all it sends the letter near the letter slot, and when it sends the letter, the LED attached at the output, the green LED will start glowing. So it indicates that there is one letter in the mailbox. Now I want to talk about one main component and some other components which I use to make this device. The first main component is Atmega 328P microcontroller. So the microcontroller basically it work for as a controlling device for the electrical system. I use Atmega 328P microcontroller. It is also working as a controlling device in the in my circuit and also in some electrical system. Nowadays, a lot in the most of the simple project, people are using Atmega 328P because it's very low cost and it's give good power consumption. It is manufactured by microchip technology, and it has 28 pins, and also Atmega has 32 KB internal memory. It can work between 3.3 volt to 5 volt, and because of its lower power consumption and some other features, it is very most popular IC in the market right now. In my circuit, Atmega is controlling the whole circuit. It's the heart of my circuit, heart of my project, and the IR sensor, two LEDs, the LCD, and the reset button all are attached with this Atmega microcontroller. Here are one more part which I used in my project, the IR receiver and IR transmitter. It is an proximity infrared sensor. The proximity infrared sensor used to detect object in the surrounding area. In my project, the infrared sensor is detecting or sensing the presence of the mail. Proximity sensor is using in we can use the proximity sensor in lots of application, like as a object detection, as a obstacle detection, and many other more. Here I use two IR sensor. It's a pair of IR sensor, and this is there are total two parts for IR sensor, one active and one passive. It's a active IR sensor. The IR transmitter is one type of LED, and the receiver is working as a photodiode. So the IR transmitter, as its name, it's transmit the infrared light, and the IR receiver, it receive this light. So when IR sensor transmit this light, it falls on the nearest object and it reflects back on the receiver, as shown in the second figure. So when it reflect on the IR receiver, the amount of resistance and the number of voltages both are changed according to the magnitude of the light. In my circuit, when somebody puts a letter in the letter box, the IR transmit sends this the light of IR transmitter falls on the letter, and it reflects on the IR receiver, and it is attached with the Atmega controller. Then Atmega controller give this signal to the green LED, and the green LED will start. Two more parts which I use, the LCD and the LED. I use 16 by 2 LCD. The full form of LCD is liquid crystal display. It has 16 pins, and as per its name, 16 by 2. It has two rows, and each rows can generate 16 characters. This is available in the market in green and blue light. The other component is LED. It emits the light when the current passes through it. Here it's my block diagram for the electronic mailbox. So there are total 6 components in the block diagram: IR sensor, reset button, Atmega LCD display, and 2 LEDs. All the components are connected with Atmega microcontroller, and all the components are getting power from 5-volt DC adapter. First of all, on the left side, the IR sensor sense and between Atmega and IR sensor, there is one later slot. So the IR sensor sends the later when somebody puts later in the later slot, and it gives the signal to the Atmega microcontroller. Then Atmega microcontroller gives signal to the green LED and the LCD display, and you can see the green LED will start, and also the LCD will show the total number of later. After this all process, when we press the reset button, this whole circuit will reset, and it goes back in the normal condition. The red LED will stay on, and the green LED will turn off. The LCD will show 0 number on the screen. Here is my flowchart for the electronic mailbox. It shows the step-by-step process of the circuit. At the beginning, when there is no letter present, at that time the red LED will stay on, and until it will stay on until nobody puts a letter in the letter box. And when someone put later in the letter box, the process will go ahead, and the green LED will start. And after that, getting the sensor value from the microcontroller, the LCD will also shows the number of the later. And when the user identify that there are later present in the box, then they can take out all the letters, and they can press the reset button, and they can wait, so the whole circuit will become reset. In my schematic diagram, I use the Atmega microcontroller as a main component. At the bottom, 2 IR sensors are connected, and the crystal is connected with XTEL and XTEL2 pin. The whole circuit is getting power from 5-volt power supply through the jack pin. The one leg of jack pin is connected with VCC, and the other 2 legs are connected with the ground. And the pins of LCD are connected on the digital pin of the Atmega microcontroller. There is one installation device which we can use to install or delete some programming data. So installation device has 5 pin. One is for reset, one for receive data, one for transmit the data, one for ground. The reset pin is connected with the reset button with Atmega microcontroller. RX and TX are connected on the Atmega with RX and TX pin. The 5 volt is connected with VCC. At the right side in the bottom, two LEDs are connected on the digital pin. And at the top, the reset button is connected with the reset pin on Atmega microcontroller. So after looking all the diagrams and the concept drawing, you can understand the important. You can understand what is the importance of this mailbox. And here I am giving you some advantages of project. So first of all, it consumes very low power. You need only 5 volt to run this electronic mailbox. So you will not get. You don't have to pay more money in your energy bill by using this mailbox. It's a very low cost. All the components are the price of all components are very low, so it's everyone can afford it. So it's a very low cost mailbox, and you can easily mount anywhere, like in the on the wall, outside of your house, outside of your room, in the college, and all other places. The main benefit of this project is it can save your precious time, and also it counts the later and also indicates that there is a later without opening it. So you do not have to go and check your mailbox. In the last, it is very useful in all the institutions, in houses, in schools, in church, in colleges, everywhere. So in the conclusion, I just want to say that as I give you some information in the beginning about this mailbox, and after showing the advantages of this project, I strongly recommend you to use electronic version of the mailbox, so you can save your time and you do not have to go and check again and again for your important mails. And also in the future, we can add a GSM model and some other additional features, so we can use this device, we can operate this device by our mobile phones. Here are some references which I used to make this project. Thank you. It's the end of my presentation. So right now, I will give you a demonstration of electronic mailbox. I have a model with me. As you can see, right now it's red LED is on because there is no letter present in the letterbox, and also the LCD screen is showing 0 on the screen. when we add later in the letter box, the red LED will start glowing and the LCD will show one number on the screen.
Your mailbox is out of frame, Lemang.
Oh, sorry for that.
And take the blur effect off your background because we can't see it.
Can you see it right now?
No. Oh. Yeah, sorry, that's better, yeah.
Yep. Yep, now it's working. So when we add later in the letter box, the green LED will start. As you can see, the green LED started. From here, I made a door so we can reset the whole circuit. It's also showing the number of letters on the screen. Yeah, it's the end of the demonstration.
All right, very good, Umang. This time I'll leave the questioning maybe some other instructors for the start. Anyways, I have a few questions, but maybe somebody else has some too. Very practical,
Sure.
very practical project by all means. Anyone?
I have a couple questions actually.
Sorry, I have some problems with the screen. That's why I cannot show it perfectly.
It's all right. Can you move to your block diagram slide, please, Iman?
Yeah. Can you see it?
No. Okay, yeah, there it is.
Yeah.
Between your IR sensor and Atmega microcontroller, there's 3 I noticed when you were doing the demonstration there, Yumang, the mail slot itself, I noticed all of the ribbon cables were passing right across the mail slot there. Would that cause any problems?
No, because when I was moving this box, it was fall down. That's why this happened, because I was adjusting my camera.
Okay. So it's not
Before
supposed to be
this
passing
presentation, I checked the whole circuit perfectly.
Okay. But where do the cables run normally? Like if
No, it's
did they
inside
move?
the box at the bottom side.
Okay. Now I'm thinking like if you constantly put letters in, you're constantly putting stress on the break.
No,
or
it is attached on the corner. So when we add later, it will not touch any later.
Okay. No good. All right. Any other questions from the other advisors?
Yeah, could you go back to your schematic?
Yeah.
I'm interested in the lower left. You have your RX and TX look like they look like LEDs. I think one of those, this is your IR sensor circuit, if I'm not mistaken.
Yeah, because the transmitter is working. It's the same functionality like LED. That's why I put the LED symbol in that. And the same symbol I found in the data sheet. That's why I choose.
Yeah, but I think what you're showing for your receiver also looks like an LED according to this, right? I think you would want to have incoming illumination or incoming radiation causing operation of your photo sensor, right? But could you, assuming that your RX is actually a photodiode and your TX is actually an LED, how does that little circuit work? I find that interesting. So it all connects to only one connection to your Atmega?
Yeah, it's on analog input pin 5.
So can you explain what happens between your RX and TX IR components when a letter is passed through the slot?
Yeah, when we add the later, the resistance and the voltage, it's changing. The voltage will increase and the intensity of IR light will increase because it's reflect back on the photodiode. And
so
because
what is the potential of I think it's pin 28 then when no mail is present?
It's in a normal condition. When somebody add later, the voltage will go high.
Normal being what? High or low?
It's a low.
Okay, and then when you have a beam break, let's say, what happens here?
Yeah, the value will increase, the sensor value for that.
Okay. So the impedance state of your photodiode, it goes low impedance, turns on.
Yeah,
that's good. Another question for you. Why don't you tell us how you programmed your Atmega? So
I watched videos on the internet and I found that I can burn the Atmega microcontroller. So I used the RX-TX pin and one register to burn out, and then I used the fresh Atmega and I add the program using the crystal and RX-TX pin.
Is there an Arduino involved in that process?
Not the Arduino kit, but I use the Arduino programming.
Okay. So that's your Jack 1, I guess. You call it an installation device?
Yeah.
Okay. It's actually sort of a
with the help of installation device, we can upload our change and do anything with our program. We can add the program or remove some parts of the program.
All right. So I guess just suggesting that maybe the name of your J1 component it might be a little misleading. It's actually a programming port, essentially, right?
Yeah.
Okay. Any other questions?
I have a few. Could you bring up your slide where you had the advantages? There you go. So their first advantage is lower power consumption. Can you tell me how you came to that conclusion again?
The whole circuit is working on 5 volt. It's only consumes 5 volt. That's why I choose this lower power consumption. You do not need more than 5 volt.
Wait. So, how do we measure power? What units do we use for power?
Voltage and resistance.
No, you don't.
Sorry,
what do
voltage
we
and current.
use to, when I ask you for how much power, which units do we talk about?
Watt.
Watt. So why are you saying that 5 volts is power? Voltage is not power, is it?
Yeah, it's no. The watt is different.
So how do you draw a conclusion that you have a low power consumption then? What do you need to know about your circuit for low power consumption?
Voltage and current.
There you go. So you've only stayed half the topic here. So you said there's 5 volts. How much current does your device draw?
It's around the 1.5 ampere.
1.5 amps?
1.5 milliampere.
Okay, so you tested that? You measured that?
No, I checked in the data sheet.
Oh, well, the data sheet has certain conditions. It doesn't, for example, include, go back to your circuit for a second there. It doesn't include your sensor. It doesn't include any of your pull-up resistors, anything like that. Okay, when those LEDs are on and off and all that, right? It doesn't, this LCD display draws current also, right? Okay, so all you have is how much the Atmega 328 is drawing, but I'm asking you what the system power is because you're saying it's low power. Okay, I think you need to go and measure and then come up to a value, and then you can state whether it's low consumption or not. All right, or low power or not. Okay, why did you use external crystal? The Atmega 328 has internal oscillators themselves. Why did you use an external crystal oscillator? And at what speed is it oscillating?
We need a clock signal to burn the Atmega.
Mm-hmm. Well, the Atmega does that with internally too. It has its own internal oscillator that does that. We in embedded the students in embedded burn the Atmega with the flash with the internal oscillator. They don't need the external oscillator. So you're saying your selection was based on the fact you needed to burn the value, the flash memory, your code.
Yeah, and it also needed for the synchronization of the whole the circuit process.
Well, again, I think you'll if you look further into the 328, you'd learn that internally it has its own oscillator circuits that
can
do that too.
8 megahertz.
Yeah, 8, and you can scale it down if you want, right? Okay.
Yep.
So that's good. You know that though. That's fine. Could you show me go forward or at the start of your presentation there? You had a few slides that were externally there. Oh, go back. Not that one. Next one. That one there. Homemadecircuit.com is your source for that.
Yeah, I took this picture
from that source.
Yeah.
Strange. I looked up that source and it tells me that the domain's for sale. So you better check that. Okay. Go to the next slide. LPROCUS, however they pronounce it, .com. You should go look up their use of content on their page. and see if you can you conform to that. Okay, also. All right, that's very important. And show me your reference page. Do all of these have citations in your reference page?
Just few of them.
Well, they should all be there. If you're citing them, they should all be here. All right. Yeah, I see you have L Proc US there. That's good. Okay.
Yeah.
But I'm weary of the homemadecircuit.com. The domain is up for sale, so it doesn't exist as far as I'm concerned. Okay, I don't know when you access that, but all right. Anyway, that's it for me. Anybody else? Ron? I don't know if Ron wants to pipe in, or Denis, or Don.
We answered all of my questions, I believe.
But kind of going back to one of your questions, Denis, when we did the project functional evaluation, I guess, at the end of last week, we talked about, and this is to you, Umang, we talked about your wiring harness sort of blocking the operation of your sensors. What did we come away? Did you come away from that discussion with anything? Any recommendations that might improve your design?
For the prototype? For the prototype?
Not the prototype. This was the finished product we looked at last week, right?
Yeah. I did not understand your question perfectly.
Okay, Mr. Legier mentioned that there seemed to be some interaction between the wires, internal wiring, and passing letters through your slot.
After
your counter or your sensors.
Yeah, after our functionality test, as you told, I attached all the wire with the plastic cap and I attached on the corner. But when I was showing for the presentation, it was a fall down. That's why this thing happened. And I also checked before this presentation that it is working perfectly or not, and it was working.
Yeah, well, it didn't come across that way, and I guess in your defense, when you use shop supplies for your ribbon cables, they really weren't long enough. They should have been longer. Your wiring should have been better organized, and suspended or fixed clear of your mail slot. So
I didn't really have another question, but can you bring up your concept drawing? Yeah, there. The dimension for the door there, the 11 centimeters, what is it really pointing to here? It's not really lining up to any of the lines shown. Is it the height from the base?
Yeah, from the base to the line. Yeah,
it's not clear at all there, but it's just an observation.
Yep.
All right. Just one last thing for me too. The fact that your project is microprocessor based, we would have really liked to have seen some of your code, and the fact that you didn't allude to it at all kind of took away from your presentation. But besides that, a great presentation, interesting device that will, I'm sure, serve you well. It needs a little bit of refinement, but most of our projects as version 1 always do. Right. So at this point, again, we're going to take another break so we can finalize the administration of this, and we'll be back at 10:30. And Mr. Avendano will be presenting on the concrete battery system analysis. So at 10:30, we will have a presentation on that. I'd also like to note that the 11:30 presentation unfortunately will not be happening. So we'll have an extended lunch period because of that. So the 11:30 presentation from Mr. Nguyen for the electronic scale will not be happening. So we'll go to an early lunch, and come back at 1:30 afterwards. So for now, let's take our 10-minute break or so and come back and see what Mr. Avendano has to say about his his concrete battery system analysis.
Sarah, I think your mic's on.
Thanks.
I don't know if it's just me, but I can't hear you, Dennis.
Sorry about that.
There it is.
My microphone kicks out when I raise the boom, and I raise it out of the way. Sorry about that. All right, so we're back from break. I'll just repeat myself, and we're about to listen to Leo Avendano talk about his concrete battery system analysis. Leo, are you ready to go?
Yes.
All right, so the floor is yours.
So before I like to get started with my presentation, I would like to give a small demonstration of what my system will be about, my product is about. So share audio. Okay, we can't share the audio, so here I'll just share the video itself. Hello? Hello, can you guys hear me? Hello?
Yeah, we hear you, Leo.
I think it froze on me. Let's try one more time. Here we go. So I know you guys can't hear the sound, but it's playing Johnny Cash, Folsom Prison. So it probably will be a concrete energy system analysis, and it's basically this use the gravity force to convert mechanical energy to electrical energy. I just wanted to show that briefly. I won't be able to show the audio though, but okay, here we go. I'll put on my camera. So good morning, everybody. Today I'm going to talk to you about my project, which is a concrete battery storage system analysis. My name is Leonardo Avendano. So I'm going to give you a brief description of what I'll be talking about today during the presentation. I'll give an introduction about where this product can be found somewhere else in the world. A functional overview where I'll be showing you all my drawings, block diagram, concept drawing, and mechanical drawing, and enclosure drawing. And then I'll show you a brief description or just a brief summary of my calculations that I had to done to determine the efficiency of my system. And I'll show the two tests that I did for my project as well. So right now, so far, in the world. There's only two companies who have developed this kind of technology, which is Gravity City and Energy Vault. The Gravity City Limited is located in Port Ellen, Edinburgh. It's in the Switzerland, I believe. No, it's in the UK. So this one's in Switzerland, and then the other one, no, this was in UK, and the other one's Switzerland. It has a height of about 50 meters high. It uses concrete blocks of up to 25 tons, which can generate about 250 kilowatts. The other one the other system is this one. There's several cranes are attached to a tower that in each crane would pick up a concrete block of about it's in total it's 35 tons of weight that the system has. And what it does, it stacks the weight whenever the demand of electricity is low, and then whenever there's a higher demand than supply, the crane picks the blocks and just lets them drop, which turns the motor into a generator. It's about 500 feet tall. It can store between 20, 35, 80 megawatt hours. And for continuous powers, and it has a capability of 8 to 16 hours. So to start off, I'd like to show you the first part of both of my block diagrams. So this was this is the first one. This is one as a motor, where you use the speed controller to vary the voltage and current going into the shunt resistor, which then goes to the motor. Now, the purpose of the shunt resistor is I was using a data acquisition to measure the input current and input voltages, because as we all know, data acquisition can only read at voltage levels, not current levels. So what I did was I used a shunt resistor, a 5 amp, 50 millivolt, which then I converted the voltage into a current level, which was the ratio was 0.05 to 5 amps. So because that was the maximum that you can measure with the shunt resistor, 5 amps. I also did measure the voltage going across terminals of the motor, and that data was gathered through that acquisition. Now, to lift the weight, what I did was I used it's one single stage of sprockets, so one that was 12 teeth and another one's 24 teeth, which we'll look at it later on. And that I used that to lift the mass up. Once I was able to gather all the data, I then analyzed it. I have theoretical values and measure values, and which I was able to determine roughly the efficiency of it with different weights. Now, this is the other generator. This is the other block diagram, generator mode. So it's the inverse of the first block diagram. So use the mass as the input power instead of using the electrical power. So use the mass as the input power. It goes through the pulleys. It goes to transmission, which is the pulley and the sprockets. Then through the generator. Then it does the same process where I measure the voltage and current that the generator is supplying to the Deca box which was part of the Deca box, which is the instrumentation that I was using to the analysis. I then also take that data and went through the DAC, did the analysis where I measured where I calculated it, the efficiency for both motors and generators. Oh, now this is the physical structure, which is a bit slightly different from what I'll be showing you later on. For this part, I had to build two different setups though, because I would have been too complicated to build one whole setup at once. So this is the big setup here on the right. It's where the weights are being held above. And then the other setup here, which will show more in detail, is the motor enclosure part of it. Even though I use a Deca box analysis part of it, I'm using a LiPo here for demonstration purposes. This is the top view of it. This is the mechanical drawing of it though. So this will be like the front side of it, where you will see on here where you see like the two set of sprockets, one here on the 5/8 inch kitted shaft, on the 5-inch shaft of the motor, and then the RBNR sprocket on the on this 3/4 of an inch shaft, which is the driven one. Over here, I don't know if you can see that, it's a bit blurry though. Here's the shunt resistor though, which is connected in a vertical position as that's what it was indicated on the data sheet for it. And the reason why I did this, it might seem a bit weird though. When I was trying to test it out first with the data acquisition, I noticed there was some electromagnetic interference causing the data acquisition to misread some values. So as a result, I decided to put the shunt resistor and the shunt resistor as close as I could to the motor, but all the electrical stuff, all the electrical components, sorry, such as data acquisition, the power, the T controller, terminal lock, I decided to put on the other side. This is the like the right view side of things without the enclosure, as to be able to see the with the 40 link change and the two set of sprockets with the V-shaped pulleys that I was using for as to be able to have like kind of like a spool, so be able to have the rope from not getting caught within the 24T sprocket. Now on the bottom here right is the actual full finished product or project, where right here on the left hand side of the enclosure is a speed controller. On the bottom here is the e-stop switch, and then up here is the it's a rocker single pole double thrown switch to be able to alternate between motor and generator mode. Now this is the enclosure drawing with more details. As I said before, this is the e-stop switch, which I didn't get a chance to draw better. And this is the inside part of it with the terminal block that I was using. The side part right here, this is where I put the all the connections going into from the motor to the terminal block, which power up the whole project. On the bottom here, what I did was I cut up the square. I cut a square. I did a cutout for the input power, where I used an old terminal power cord. And on the bottom here, I did another cutout, but that was just for the ground cable, as it was easier to connect things around without overlapping too much. Now for this, I realized that I wasn't able to submit a wiring diagram on Friday, but this is what I was able to finish up before presentation. So as I said before, I use a power core, an AC power core from an old terminal. I connected the block to the e-stop switch, which is a double pole single throw switch, normally open, normally closed. So one side of the hot wire, the normally closed switch, and then the other side to the speed controller. The white wire is like the neutral wire connected to the AC2, the speed controller, and obviously the green is connected to the ground. It's grounded with the motor ground as well. The other set of contacts for the e-stop switch, I connected them directly to the e-stop terminals on the speed controller. I did try to look up online what PW stands for, and the only thing I come up with is pole width, which I believe it's wrong. This is the lamp that I used for the lamp that I'll be using for the demonstration, but I also did use it for testing purposes. I did not place that. I did not name what this switch was, but it's supposed to be S2 because the e-stop is S1 and the switch to switch back and forth between modes is supposed to be S2. I know that normally we use like a red wire for plus sign going to the motor, but I use 3 different colors here: blue, red, and yellow to be able to differentiate easy. This R1 is the shunt resistor that is, like I said before, it is used to measure the current, the voltage across of it to be able to determine the current supply to the motor and the current generated by as a generator. Right here where it says M1 is the motor. I connected channel 2 to the motor, so red to black, and then channel 1 to red to black. For simplicity of the drawing, I just decided to draw the 2 channels. All the wires that I use for this project is all American 16 gauge wire, and I did that just to be consistent, as that's what the motor had for the leads. Part of the calculations which I wasn't able to complete as I didn't do it properly was I wanted to determine what was the rated torque for how much my system can lift as a motor based on the rated torque. So as some of us might remember the rotating machines though, if we have torque is measured by force times the radius of the shaft. So I rearranged the formula to determine what's the maximum force in newtons. And then I was able to determine like the maximum weight. So I knew how much I had to work with, just so that I can test it with different electrical loads, but at the same time test it with different mechanical loads applied to the shaft, applied to the whole system, sorry. And this is these are also like the formula sheet that I had developed though when trying to determine the efficiency during each test. So on the left hand side will be as a motor. The rise time, it is referenced to the fact that it will be from the bottom of the weight to the lowest point that it can hit. The weight will hit the structure, or like on the base of the structure. The rise time was measured or was determined based on the fact that you would take from the adequacy, you would take your final reading time minus your initial time, and that's how you're able to calculate your linear velocity. Oops. The force then was determined based on the fact that I did weigh each set of weights that I was using for doing my project. I had to determine since everything was given in inches, I had to convert it back to meters just to keep everything metric. Then once I was able to convert the diameter of the shaft into radius, I was able to determine the torque of the motor. Yeah, so based on the time and the torque, based on the time, I was able to determine the RPM, the angular velocity in rads per second. Then I was able to determine the RPM, and then okay. So based on this, I was able to determine the efficiency as a motor and as a generator using all these values. Okay, the next one. Okay, so this is what I meant. What I was trying to say. I had to calculate the RPM and the torque in the whole system. I neglected the losses of the pulleys just to see how the math would work, I guess. It's also part of the math. Okay, so for my first test, what I did was I used a Prony brake. I had to determine what I wanted to determine what the parameters of the motor were, like the basis, so like efficiency, power in, power out, and the torque. So I first started out with no load. Then I slowly increased. I slowly adjusted the load adjustment, the knob, every 200 grams, as close as I could, because it will vary, because the scale will vibrate. But I did try to get as close as possible, and that's where I took the RPM readings with the tachometer. I measured the current and voltage with 2 multimeters, and the reason why I did that is because the data acquisition was limited to only 50 volts full scale. So therefore, if I wanted to test if I wanted to find out the parameters of the motors in the graph, I had to use the multimeter because I was running it at 90 volts, which was the rated voltage, the rated armature voltage, and the rated current was 3.7 amps. So, and what I determined was that the highest weight I could go to was the highest mass in the low scale was about 1.1 kilos. So this is one of the graphs that I was able to obtain. Left hand side is the RPM. I was actually able to go a little above the rated RPM no load. And then on the right hand side is the efficiency of the motor. And on the bottom is the torque in Newton meters. For this one, it was I wanted to be able to have like all the parameters in the same graph, but it was too complicated, and I wasn't able to perform that on Excel. So in this graph, I have the input current. The input current, which was I got around the maximum. I think I was able to go a little higher. Yeah, I was able to go a little higher than 3.7 amps. But I was not able to determine like the stall current. On the right hand side is again it's the efficiency. For this one, this is the power out versus efficiency, and I guess where I should have operated the system at the most optimal point would be like around 0.6 Newton meters. So this is like the kind of like the block diagram of how I did the first test of my system. There's other losses in the system that I could have determined, but I did not determine, such as like hysteresis losses, core losses, and iron losses. This is the second test that I did though on my system. What I did is I varied the mechanical load. So I went I had 2.5 kilograms, and it gave me an energy of about 95.59 joules, which ends up turning 9.56 watts. That was input power as a motor, and in the output power, I would get like 3.87 watts for a time of 10 seconds with an efficiency of about 42.52%. And then as a generator, I would get about 14.49 joules of energy, and the power coming in as the weight would come down in this case, because it would have inversely. So therefore, instead of being as a generator, instead of being the mechanical power, instead of being the input power being a electrical power, it is mechanical power. So therefore, as a result, I have 4.21 watts. And as P out, I had at P out as a generator, I have 1.57 watts with a time fall of 9.2 seconds and an efficiency of 37.41%. For 5 kilos, I had 163.18 joules of energy stored as a motor not storage, 163.18 joules of energy used to lift the mass, which resulted in 13.16 watts of power being used. And at the output, I was able to get 6.25 watts with the time to raise the weight of 12.4 seconds, with an efficiency of 46.48%. For a generator, though, I was able to get at for a generator, I was able to have 35.4 joules with a input power as a generator of 18.45, and power out as a 8.43 watts with a time fall for the mass to fall down for 4.2 seconds and an efficiency of 45.69%. The third test that I did was a 5.25 kilo, which was almost like the limit that I could have done because of that acquisition. I was getting around 49 volts as a generator. The energy that I obtained as a motor was 164.92 joules with a power in of 12.88 watts and an output power of 6.36 watts with time to raise at 12.8 seconds and an efficiency of 49.3%. And then these are the results that I have for just not to be repetitive, these are the results that I got as a generator. This is my part list, somewhat quite long. These are my references, and then I will be showing a demo of my project. Should probably stop sharing my screen. Here, I'll do it again. Can you guys see full screen?
Yes,
you're completely to the top of the rack, but I think we're pretty good.
Okay. I think it's just someone sharing their screen, I think. Can you guys see from this angle now?
I don't see anything. It's black.
I don't see anything either.
No, sorry. It's I'm using my. There.
Oh, there it is.
Okay.
And then there's also this angle. Can you see the other angle?
Yep.
Yeah. So that's the stop. This generator. And then here's the DAC. And I'll show you guys briefly the inside of it. Is that, hold on, sorry. Yeah, there we go. Yeah, and I guess that would conclude my presentation. Any questions now?
Thanks, Leo.
Yeah, no problem.
I guess I can get started. Maybe I missed it, but how does it work exactly? Like, what's the functionality of the system itself? I don't hear you. I can't hear you there.
So my goal was to determine the efficiency of the system between a generator and a motor mode. So it was basically
Leo, can you explain what your system does? I don't think your video to start wasn't very good at explaining what
No.
your output. You talk about efficiency in that,
Right.
but I think that Mr. Lizard is not the only one that really doesn't understand what your system's supposed to do. Okay, that's I know you've been involved with it for the last several months, but I think you may want to just tell people what was your goal, you're measuring efficiency of what though,
Yeah, so my goal was to determine which system is more efficient is as a motor or as a generator. So determine the input power, the electrical input power versus your output mechanical power, but also determine how much energy it is stored while the way it's being held up in the air. For my system, I wasn't, since it was an analysis part, I didn't involve a limit switch to keep the weight held up. So I had to manually switch it whenever the weight raced all the way to the top.
Leo, take a step further back. Where would you use? What were you trying to simulate with this system? Where does industry use this system? Or would you use
power.
this system? No, but
power.
where would they? What is the purpose of, let's say, NB Power wanting to use something like this? You're getting into the finer details without explaining the basic concept of the system. Okay, never mind your system. You showed video of other systems. What is the purpose of these systems? What are they trying to achieve?
because we're trying to maybe find a more a better renewable system for storage energy, because like lithium batteries, they only have a certain lifespan based on how much you charge them, based on how much you discharge and charge them. But a system like this at a larger scale, it is said that it can last 25 years without any degradation from having to do any, compared to chemical batteries.
Well, Leo, my main question is just that looking at your system and not really understanding how it functions, like I'm looking at it and I see an engine that's pulling weights up and down,
Right.
but what's the purpose of it? What is it? Why is it doing that? And what's the outcome of it? You showed me results and stuff, but the basic explanation was never really explained.
Yeah, so I guess where a system like this would come in handy though is, for example, wind turbines cannot function all day, all year round, all day long when there's no wind, or solar panels cannot function when there's no sunlight. So whenever you have more demand than supply, a system like this would come in to like help supply the demand for example, I know New Brunswick here, but for example, something happened recently in Texas, and when the power went out because the wind turbines froze, and a lot of people were demanding a lot of heat. A system like this could help level off the demand and supply, and therefore would not cause a huge brownout for weeks.
So how would it do that? Again, at the utility level, how would it do that?
Sorry, can you rephrase the question?
How does it provide the ability to level off, in your words, level off the energy demand, okay, on the plant, all right? In other words, on the utility. So you have customers that want energy, okay, but at the moment maybe we have to set up peaker plants or things like that to meet this demand. How does your system alleviate that need? How does your system, in your case, you were simulating it, but how would your system alleviate that need at a greater scale?
So, for example, when you have high demand or a high supply below demand, instead of just shutting the plants off, you can just direct all the electrical energy to the system like this. Therefore, will cause the waste to raise up, and then you store that energy. And then whenever you have the opposite, the inverse, whenever you have more demand than supply, you will let the system run. You will let the weights come down, and result, you will get not all of it, but some of that energy back from mechanical to electrical.
And thus acting like a
Generator.
No, acting like a overall. If I can put energy into the system, store it, release it, it acts like a what?
As a battery?
There you go. But
Yeah.
not a chemical battery, eh?
No.
What kind of battery?
Potential mechanical?
Yeah, potential or mechanical.
So extra energy raises the weights, and then if energy is wanted from the system, it slowly drops, which generates power to power something. Okay.
Exactly. And the speed, how the weight drops is based on your losses within the gears, or your load. It's based on what electrical component it's connected to, because the higher the resistance, the lower the speed. So in the case with the disco player, power in disco, the disco player being powered by that gravity system, the higher the volume, the faster the weight would fall. But the lower the volume, the weights would fall slower because you increasing the resistance. So
Okay.
So in my case, the motor, what's causing what's causing the system to go slow is the weight. So therefore the motor would try to overcome that weight by increasing the current, because as we know, current and torque are proportional to each other, and RPM and voltage are proportional to each other as well. I don't know.
Thanks, Leo. Any other questions?
I have a few. So I guess the follow-up question to that is, where's the concrete in your battery?
It's for my demo. I used plates from dumbbells. I switched them because I realized that the ground power clock's weight, it wasn't going to work. It wasn't going to work that great. So this is the one that I wanted to use. That's the one I put in my drawing, but I realized it wasn't going to work that great. So for better demonstration purposes, and I also did them for the analysis, I used the dumbbell plates.
Okay. Did you ever consider maybe looking into, again, we call it a concrete battery because I think
Yes.
the functional ones actually use concrete. Did you look at what would be better materials?
A material with a higher density.
Such as, did you look at other materials?
Yes, because I was trying before I bought the ground power clock piece, I was trying to see what material had the highest density. I think it was plutonium was one of them, silver, gold, all those rare metal materials that had a higher density.
But what's the trade-off?
Price, cost.
Some of them radioactive emission.
Exactly.
All right. What I appreciate your analysis slides. In fact, I really like the overall. You determined some efficiencies in that. Although I think you took a lot of averaging, which may have led to some numbers not necessarily being dead on there.
I actually did like on Friday after you spoke to me. It all makes sense, and the numbers started making sense. So the numbers on my PowerPoint are from taking the voltage and current, multiplying them, and then times the power times that time interval to get your energy. Sum them up.
There
you divide that by your total time, and that gives you your power.
Okay, that's fine then. The question I'm asking though is, overall in the end, when you had all these values, you gave us here's the efficiency going into it, here's the efficiency coming out of it. What about, this is an energy storage device. So what about the overall efficiency once you're done? When you put power or energy into it, you store it and you release energy back out of it. What are your percentage expectations of getting the energy back that you put into it?
Well, when I did my testing, that's what basically I did though. I raised the weight. I took that data from that acquisition and did the math. I did it as one file. So I had to break the file into two sections to determine, okay, this is the motor, this is the generator. And that's how I determine, okay, as a motor, it has this efficiency, and as a generator, it has this other efficiency.
Okay, but I'm asking, what's the overall efficiency? Do you understand what I'm saying? Imagine a battery. Instead of your system, imagine a battery. I put energy into the battery. It's got a certain amount of efficiency. When I draw energy from the battery, it's got a certain amount of efficiency. But if I look at what I started, how much energy did I put into the battery, and how much energy did I get back from the battery, that's the overall efficiency, which is the combination of both. Did you have an opportunity to test that or evaluate that analysis? I think that's the number that if you're going to talk to utilities about, as concepts and that's the number they're really interested in.
23%.
23%. Do you think that's high, low? How does that compare?
By itself, it's very low. But if you were to use other renewable energy sources in combination, then you would. It won't be more efficient, but it will make more sense. On its own, that's not a good efficiency. But with other systems combined that don't work when there's no sun or when there's no wind, then yes, it'll probably be more efficient.
Well, it's more efficient than nothing, right?
Right.
Right. It's more efficient than nothing, right? Because other systems that try to do the same thing, such as the battery and whatever, they have their own. Again, as a system, they have their own issues of efficiency too. Because you've got to, if it's a battery system, you have to convert from AC to DC and then back DC to AC. And again, when we start looking at system efficiencies, that's where you should be doing a comparison to other systems and be saying, well, okay, mine's not great and it's very limited. It's a small setup. You didn't have too much time working on it. But the reality is, if I compare it to other systems, is it in the ballpark? Right? Are other systems at 30, 40%? Well, okay, well, that's not that far away. Or if they're at 80, 90%, well, that becomes, and we saw that somewhat when you took your PV course and we talked about batteries. We talked about battery efficiencies being 80%, but, we can't draw. That's the release of heat when we're trying to charge the battery and that. But the reality is we can't draw from the battery 100% of the energy either, even in a deep cycle, or it'll damage it. So then, we take 50% of that. And so that efficiency number, once we're actually doing installs, rolls up to be not that great either. So again, I think it would have been a really good analysis results, which you should have had in your conclusion, which was very brief, that, hey, here's how it compares to the other systems. Because that's the selling feature of this, is to try to replace some of these other systems in its simplicity and its ability to store energy, right?
And then the cost to build one would be very low if you were to use old mine shafts. I kind of looked at them, but I think there's around 100 mine shafts across New Brunswick. So the only thing is it'd be a private property. So,
well, again, that's part of the deal, right? So, all right. Anybody else have other questions?
I'm good.
Nope. I was looking for that overall efficiency conclusion, so thank you, Dennis. You covered that.
Well, I think that's the whole goal of this project, is to at the end be able to compare to other systems and say, is it worth pursuing or isn't it, right? I mean, you did a good job in explaining that you had efficiency loss, or you had losses that were hurting your efficiency, and there were some that to be honest, you should have been able to calculate and determine. And I think like you said, when you generate versus when you lose, you can easily figure that out. But then you need to combine the two, come up with a number, and then do a comparison. It's all about comparing, right? Okay. All right. So if there are no more questions, we'll stop there for now. We'll go off to lunch, and like I said, we'll have an early lunch because we've got one presentation that's not going to happen this morning, and we will come back at 1:30. And at 1:30, we will have let me get my schedule out here. We'll have Mr. Silviera talk about his PV panel solar tracker at 1:30. So that should be interesting. So everybody's invited back to participate. And just a reminder, the presentations are recorded. So if you cannot make it back, they will be available afterwards on the YouTube as a recorded stream. So you can go back and take a look at them at your best time and location. So, and again, if you do have problems with the stream, let us know. We'll be glad to try to fix that for you. All right. We would really like some feedback on that. Right. So if nobody else has any other comments or anything like that, we'll break for lunch and come back at 1:30.
See you guys later then.
Instructors, can we meet in the other chat room just quickly?
Sure.
Sure.
All right. I hope everybody had a good lunch, and we're back for the afternoon of day one for sessions. We have 2 more presentations today for sessions, and I hope everybody's prepared because I think we have 2 pretty good ones. All of them are good ones, but anyways, these ones here were advised by myself, so I think I have a little bit of insight as to the content. So we are going to start with Mr. Marconi Silveira, who has, who has a PV panel solar tracker project that he is going to inform us all about this afternoon. So Marconi, if you're ready.
Yes, I'm ready.
The electronic floor is yours.
Okay, hopefully. Okay, good afternoon, everybody. Can everybody see me and hear me? Yes, no?
Yes, yep,
yeah.
You're good.
Okay, great, perfect. Okay, I'm gonna share my screen. Can everybody see my screen? Can you see my screen?
Yeah.
Okay, good. Hi, good afternoon. I'm going to start with this citation here. Solar power is going to be absolutely essential to meeting growing energy demand while staving off climate change. Hamesnaam. And I completely agree with his statement. And I think that if we already have the technology to harness the energy from the sun, such a powerful source, why don't we, as engineers, technologists, and scientists, don't try to focus on find more affordable and efficient ways to use this technology? So with this in mind, I got the opportunity of the project, of the SPL project, to apply the knowledge that I got so far in the alternate energy program to try to develop a device which could improve the use of a solar panel, but just using electronics components, but not programming or microcontroller stuff, just the simple electronic components. So this is my project, PV panel solar tracker. And as Mr. Metcalf said, my name is Marconi Silveira, and we're gonna talk about that right now. So what we're gonna see here, we're gonna answer these questions here. What is the project? How does it work? What were the challenges and solutions? And how is the project today? So first question, let's answer the first question here. What is the project? Well, the project is a mounting base for PV panels which tracks the sun. So we, as you can see here, we have this base here, and we can fit a solar panel here inside, and the base is going to track the sun in just one axis. In the vertical axis, it's going to turn to the left or to the right or east or west by using just these 2 phototransistors here in the top of the panel. I'm going to show further more details, and it's going to try to keep the panel facing the sun throughout the day. And despite it only tracks automatically in one axis, in the vertical axis, we can adjust manually the tilt angle here. I'm going to show more details. And this is just a concept drawing because there are much more information to show. But here you can see the enclosure where the PCB goes here. Here we have the DC motor which is connected to the flywheel here. This flywheel is connected to the pole, the master here, that's gonna turn the panel to left or right. Okay, so how does it work exactly? So here, I'm gonna start here in the top. The system, the device, is powered by the 9 volts battery here, and this 9 volts is stepped down via a voltage regulator to 5 volts to provide power to the electronic components here in the brightness comparator circuit and in the motor directional controller and protection. Why did I step it down this voltage here? Well, the most of the electronic components that we have here, they are tested in 5 volts. So the most of data that we have in the data sheets, they are tested with 5 volts. So it's much more, how can I say, much more easier to understand what's going to be the behavior of the components, because they already were tested with this voltage. And the second point is that we can have a much more stable power to the components, because if I connect it straight the 9 voltage here, the battery is gonna vary the voltage, so it could affect the electronic components here inside. But we can see that the 9 volts also provide power here in the directional controller, motor directional controller. But because this 9 volts here is gonna power the motor, but it's gonna power the motor controlled by the 5 volts in the IC here, the LM298. Yes, is a bridge. So in here, you can see the sensors. So the sensors are going to get the power from the sun. It's going to get the light from the sun here, and they're going to compare these values here. It's going to vary their resistance here, because these two sensors are two phototransistors, which varies their resistance according with the amount of light it's seen here. And this variation here generate an analog signal that goes to the brightness comparator here, and the brightness comparator is gonna process this analog signal to a digital signal and control the motor directional controller actually. Okay. And just a small detail here is that to show that the enclosure where the sensors are mounted, there is a shading divider here, because this shading divider is the most important point to the sensor, because once I have more light here in this side here and a shadow here this side, the resistance is going to vary here, and this data is going to be processed by the brightness comparator circuit, and it's going to control the motor to move the panel towards the sun, the light. So what were the challenges and solutions? Did it work? The first question is, did it work as expected after assembly? No, unfortunately, not the first time. And what was the problem? Well, the first problem, because I had more than one, was the inverse operation. What do I mean by that? When I finished the assembly and I turn on the device, the solar tracker was running to the opposite direction from the light. It was running away from the light like a vampire mode. So that's what my first problem. It was operating in the opposite mode. So, and the no dark mode. What I mean by no dark mode? The dark mode, I mean, at the end of the day, when after the solar tracker follows the sun until the sunset, it's going to be dark there. So if I didn't figure out how to bring it back to the sunrise direction before, so it would not follow the sun again if I didn't bring it back. So this was the other problem. And the third problem was the no motor protection. What I mean by that is I didn't set any circuit protection to prevent to damage the motor if we have any surge of current. For example, if the motor stuck, or if even during the movement we have some surge of current, it could damage the motor. So what were the solutions that I found to solve this? The first point was I reversed the input polarity in the op amps here. And by the way, I'm using an LM324 with 4 op amps in just one enclosure. So I noticed that I put the reference voltage here in the positive, and the other side, the analog signal was connected to the negative side. So when I have higher voltage here, it's going to stop, and when I have a lower voltage here, it's going to move. That's why it was operating in the opposite situation. So what I did was I figured out that was the problem, and I flip the connections here, and it worked. Good. And the second solution was for the dark mode. How could I bring automatically back the solar tracker towards the sun at the end of the day after the sunset? To explain that, I need to explain how the L298 works, because this is the motor directional controller here. It works this way. It has 4 inputs and 4 outputs, where I could put in parallel 2 by 2 inputs and 2 outputs, so that I could deal with a higher current for the motor. And the output's gonna obey what the input do is. If I have 2 signals at the same kind of signal, I mean, if I have high and high or low and low, the output's gonna be stopped. We will not have the output working. But if we have one input on and the other high and the other low, the output's going to be okay. It's going to work in one direction. And if we have the opposite situation, we're going to have the opposite direction of the current in the outputs here. So what I did was, first I need to explain here how the operation of the motor works during the day. So when the light is reaching the phototransistor here, the voltage is going to increase the input here, and is going to turn on the op amp here, and automatically it's gonna provide the high signal to the one side, and the other side probably is going to be already on the sun, on the light, is going to be off. So this is going to make with the motor turns towards have both sensors under the light, so off and off. And there's one detail here, as I mentioned, and I use an LM324. I have 4 op amps in just one enclosure, so I got the advisor's opinion, suggestion. It was perfect because I was leaving this open there. So I'm using these 2 other op amps in the follower mode. What is that? It's gain 1. So the voltage that I have getting in here, I'm gonna have getting out here. The voltage that I have coming from the first gauge here through this input here is gonna be the same value here, and it's gonna follow what's coming here. So I'm using this one to provide the inputs for this part. So what I figured out to make the motor turns back was I created a conditional short in this output here. So if I have, even though I have a high signal here, if I connect it to the ground, I'm gonna have a low voltage here. So even though I have on here, this point is gonna be low because it's straight connected to the ground. So how I did this? create the conditional short here. I put two transistors where they are going to be closed only when I have both on. And in which situation I'm going to have this happening? When I have the dark situation, because I have on and on here. So this is going to close this path here, and it's going to short this path here straight to here. So I'm going to have on in one side and 0 in the other side, even though I have on and on in the inside here. So it's only going to happen when I have both on the dark situation, and so it's going to turn the motor back to the other direction. And I put a limit switch here in series with these two transistors, so that once the solder tracker reach the sunset position, it needs to stop, because otherwise it's going to keep running, keep turning. So when it's reached there, it's gonna open this limit switch, normally close limit switch, and the system is gonna work normally again, waiting for the light of the sun in the next day. And yes, that was the short. Those were the transistors that I used. And the last issue that I found was the protection for the motor. And what I did was, well, here is the motor taking the output from the bridge here, the LM298. So to be able to, if I have any surge of current here, probably it's going to damage the motor and going to damage the L298 as well. So what I did was I used a LM311 here and another op-amp to compare the voltage in the output here. I forgot to mention, this is the output from that comes through the motor, goes within the L298 and goes to the ground over here. So this ground here, because I cannot show here unfortunately, but there's a resistor here, a power resistor here with a really low resistance, 0.0 ohms only, just to be able to get a small voltage here in the output and use this voltage as a reference to the 311, so that I can operate in case of a high current goes here. Because if the current increases too much here, the voltage is going to increase. So I'm going to have a higher voltage here than the reference voltage, and I'm going to have a reference of voltage here. So if the voltage here is going to be higher due to some surge of current, the output here of this op-amp is going to open and it's going to stop to power the enable of the L298. I forgot to mention that this is controlling the enable of this L298. So this was I did to solve these problems. So yes, I forgot to show the arrows. So how is the project today? This is what I have today. After I finish everything, after I do the assemblings, after I use the jumpers that I needed to use, because I have a lot of components to put in just one layer. So I had some hard times, Mr. Metcalf as well, to do this, but I did, and this is the final version here of the prototype. So everything's set. Oh, well, one important point here is that when I did this setting here, I connected the base of the transistors. Even during the low situation here, the transistors were activated, both, even low and low. And I don't know, it took me some time to figure out what was wrong. I noticed that even in low situation, we still have some leakage of current here. And the small current that we had here was enough to activate the transistor here, to close the transistor. So I needed to put two Zener diodes here to vary this current. And why did I use 2? Because I tried with 1, even 2.7 volts. Oh, I forgot to mention, in low situation here, we still have some voltage here as well. It's about 1 volt, I think. Yeah, it's about 1 or 1.2 volts. And this voltage also is enough to activate. But even though I put in 2.7 or 3.9 or 4 volt Zener diode voltage, Zener diode here, I still had the transistors working because, as I said, because of the current leaking here. So I tried to put 2 Zener diodes in series, and it worked finally. So this is how the project is after the PCB be assembled. Here we have all the components in just one layer, and here is the PCB when I was testing it out of the enclosure, just with the connections of the battery, the sensors, and the motor here. And this is how it looks like today after everything is assembled. And for the conclusion, what I would say is that after hard work, it's worth, because the main point here is if I can have this technology in an affordable way. Because why I'm saying affordable? Because I'm just using some few components, some transistors, connect some resistors, and I'm able to improve the use of a solar panel just with this simple components. I can make much more affordable and this kind of technology for more people if when I finish completely the prototype, because it's just a prototype. And that's it. I'm gonna trying to show the prototype working now. Let me just to turn on the other camera. Just a moment. Sorry, I don't know what I'm doing wrong now, but the other camera is not working, so I'm gonna show with the laptop camera. And just a moment. Sorry about that. Can you see my camera?
No.
No, yet, not yet.
No, I don't see anything right now.
Okay, sorry.
It was on a second ago, but now it's off.
Yeah, we could see your the ceiling there.
Oh, the other camera was working?
I believe so. We were looking at the ceiling and we could see your laptop actually. So.
Sorry, I don't know what's wrong, but okay, I'm gonna use this one here. Sorry. Okay, finally. Sorry, can you see the device?
Yes.
Okay, finally. I'm gonna try to put it over here. Sorry for the bad quality of image. Okay, what I'm gonna try to show is that right now it's turned off. So in this direction here, I have the brightness light. So I'm gonna turn on and it hopefully is gonna work. It needs to point towards the window. Yes, it's working. So if I cover the sensor, it's gonna turn the left until reach the limit. And if I turn the hand over, it's gonna go back. And even I'm gonna simulate like if the sun is moving around. So I'm gonna turn the base. It keeps adjusting towards the window. Can you see this?
Yes, we can.
Yes, we can. Yeah.
Yes. So if I cover, this way it's just reached the dark mode. So it's too dark to the sensors, that's why it goes and stops, because it's reached the limit switch and stop. In the other day, when the sun appears again, it's gonna follow the sun. The same way throughout the day. And this is my program. Okay, thank you everybody for your patience.
Thanks, Tony.
Yes?
I was just saying thank you for the presentation.
Thank you for your patience.
Does any of the instructors have any questions they want to start off with?
Not just yet. If you have one, go ahead.
Okay. Excuse me. I have a few questions. Can you go to the your schematic, one of your schematics there?
Mm-hmm.
I really appreciate the fact you had multiple schematics there, adding to the stages there.
Yeah, it's gonna be easier to reference. Yeah. Let me just reopen here.
Sure. Maybe that a lot. Yeah, that one there. Okay. Just if you can talk about, could you? I want you to talk to me about U1A for a second. You talked about the fact that you had to switch the inputs, and you used certain terms that I just want to revisit there. Could you just maybe explain to me what you did to switch the inputs, and then when you use the terms, I'll stop you at that point.
Okay, sorry. When I'm talking about this part here.
Mm-hmm.
Okay. So the variation of the light intensity in the phototransistors is going to vary the resistance, the voltage here. In this, I forgot to mention this. These trimmers here, these potentiometers here, they works for adjust the sensitivity of the sensors.
Mm-hmm.
So once the voltage, the resistance vary here, the voltage in this point is going to increase. Okay, because if I have the dark situation here, the resistance is going to increase, and the resistance is of this part is going to add in series with this part of the potentiometer, and the voltage in this point is going to increase, and consequently is going to go be higher than the reference voltage here. The values that I didn't mention was, sorry?
Could you name those two terminals for me? Pins,
those here, those inputs?
Pins 3 and 2, what are they called?
Oh, non-inverting input and inverting input.
Okay, thank you. Because you used the term, you talked about polarity and the positive input and the negative input, okay, during your presentation.
No.
I'm going to chalk that up to nervousness, but obviously we're not talking about polarity, right? We're talking about
no.
Inverting and okay, that's what I want to clarify on that. Also, you talked about the output of U1B, I guess, and U1C, pin 7 and pin 8 there.
I'm gonna make a little bigger here in presentation just to make it easier for me too.
Sure, there you go.
Make it easier for us.
Next, yeah,
yes.
there. Yeah, so let's talk about pin 7 and 8 of U1.
Pin 7 and 8.
The outputs of the two of U1B, U1C.
Oh, here and here. Okay.
Yeah. Okay, so you said there was a voltage that remained on that output even if it was low, right?
Yeah.
Could you think about a reason why that was happening?
Yes, I think even though we have low here, okay, we have this path here.
No. Did you look? Well, obviously, you must have looked at the specification of the LM324.
Oh yeah.
The spec sheet, sure. Did you notice if the 324 is what's called a rail-to-rail device, or is it, how close can the output go to the supply voltages?
Okay, it's 32. Let me see here. I have the data sheet right here. The input, right?
Yeah. Well, no, the output. How close can the outputs go to the rails or the power the power pins, right? Because you get two power pins. You got one that's the positive supply, and you've got one that's a negative supply, right? Mm-hmm. You chose to ground it, but it's still the negative supply.
Yes. So I can see the higher voltage that it can goes, but not comparing here, because the higher voltage is 26 volts, but it's not the situation.
Yeah, no, that's not the specification I'm looking for. I'm looking for basically how close, right? The output itself.
The voltage here and the voltage here. Okay.
Yeah, it can go. No, the output itself, pin 7. Okay, the output voltage can only go so low, and it only goes so high, right? And it's a factor of the supply voltage on pins 4 and 11. Okay, and in that spec sheet, it's going to tell you how close it can go. All right, and I would suspect that it doesn't go to what's called a rail-to-rail, which would go within millivolts of the upper supply and the lower supply. Okay, I don't have the
difference between them. Okay.
Okay, and because of that, that means that when you go low, well, if 0 volts is your lowest point, Okay,
Should
you
be,
can't get it. You can't get close to that within probably a volt and a half. That's what you're saying. You're saying you were always getting a volt and a half. Okay, so the way there are ways to deal with that. You could have gone online and looked at some. I didn't realize you had that issue. Okay, during the development, had you had that issue, we could have gone online and you could have found or a textbook, right? And we could have found a solution to that would have allowed you to go to closer to the rails. All right. I'm trying to find.
Probably if I had figured out this before, I would not need to use this.
Well, yeah, exactly. The diodes wouldn't have been so critical. All you did with the diodes is you added voltage drop at the base, right, to force the transistors to go on at a higher voltage level than the zero that you expected, right? Okay.
Yeah, that's true.
So that's all you were doing there. Yeah. So again, op amps typically don't, unless you buy the correct op amp, they don't go rail to rail. They go to a limit that's close. What you probably would have wanted here instead were comparators. Okay, for the second part, the output. Okay, but then you would have had another IC, and you were looking to make this cheaper, right? So with a comparator, that would go to a positive supply or negative or a 0 volts in this case, due to the nature of how the outputs work, as opposed to an op amp. All right, so that's one big distinctive difference between op amps and comparators. Are that the comparators allow us to go to a positive or negative value that's set, or we can set, whereas the op amp, it's really more of an amplifier, right? So it goes in between those levels and doesn't always work the way we want them to.
Okay, good. Now I know. I learned.
Now you know. Yeah, there you go. Now you know. Anybody else have any questions there?
Well, I'm just noticing, since we have the schematic up here, around U2 here, the L298, why are there so many jumpers surrounding
that? Yes. First, because I as I mentioned, we have 4 inputs here, okay? But I could combine 2 by 2 to get a higher current. So the first 2 jumpers here, I'm jumping 5 with 12 and 7 with 10, but I didn't use jump just for this 2 here.
Okay.
And here 2 plus 4, but actually it happened because when I was assembling the PCB, I didn't have enough space, maybe even I have too much components to put in just one layer. So I needed to reorganize something, and I needed to use more jumpers than if I could use both layers, if I have been using both layers.
Okay.
That's why I have too many jumpers.
Yeah, I counted 8 just around that.
Yeah, exactly 8. Yes, I have exactly 8.
That's a lot.
Count it right. Yeah, 8.
I noticed too, I think R8 was added after the fact, right? You said that was added on the bottom right there, I think it's R8. Yeah, the 0.5 ohm resistor.
Just some. They are jumpers. Just
not the jumper. Resistor. The it's far right corner, bottom right corner there on its own. Yeah, right there.
I cannot. I only can see your camera. Okay. Yeah. Okay. This is the power resistor. This resistor is used just as a sense resistor, just to feel the current, to measure the current that's flowing here, not the current but the voltage.
Right. No, I just noticed the symbol's different from all of the other resistors. Is there a reason for that?
Yes, that's a power resistor.
Okay. Perfect.
Why did you use a generic symbol for R8 and not the US version that has all your other resistors?
Yeah, my mistake.
Okay.
When I was using the Eagle, I found this symbol here for power resistors, and I use it. But you're right. You should in US. I think you have the right one.
All right. Any more questions, Denis?
Not really, no. No,
I
think
do have. Oh, okay. I do
sorry,
have
go ahead.
another question, I guess. In the operation of your circuit as it's tracking, I guess what I would have really liked to see in your project is a way of justifying the added cost of your tracker. The reality is today trackers are kind of not necessarily used a lot in certain scenarios. Certain scenarios they're still used, but in a lot, because what happens is it's just with the cost of PV panels, it's sometimes just easier to add PV panels over the tracker technology, and it's, again, less moving parts, the better long run maintenance wise it is. So I think what I would really want to see is, and I know you haven't done testing yet, but I would have maybe liked to see a theoretical comparison of how much energy would you gather during let's say an ideal solar day, and then how much would you get by tracking with your device, how much more energy. Did you have an opportunity to actually do that, or?
Not yet, but it's part of my tests.
Yeah, that's fine. It's just, on the theoretical side too. You've taken a PV course, you've taken a solar hot water course too, where we both talked about a lot about the available energy from the sun, and I think you could have come up with some numbers easily that would have said, hey, if you use my system, you gain 30, 40, 50% more technology. Or more energy, than if you don't use my technology, right? So that would have been a little bit of justifying the values. Okay. Somebody's asking about the two diodes in series D8, D9, and D10, D11. I think it's Mr. Broad. I'm not sure there. So could you maybe reiterate the reason why D8, D9, D10, D11 have to be there?
Oh, yes. As I mentioned, even though I have the low output here, I still have some small voltage and current as well. Pretty small, but small and high enough to activate the transistor when it should be off. So that's why I put the Zener diode here to prevent this voltage and current to activate these transistors.
I guess the follow-up question was actually, why did you use two diodes instead of not using one single?
Okay, actually it was by testing, because I did it with one, but it didn't work, because I noticed that I still have some current leaking from this to or some voltage leaking, I think. No, current. So when I tested with two Zener diodes in series, it stopped.
Okay, but why didn't you to keep the parts count down, which is always a concern as far as developing a device, which you, by the way, something else you didn't mention was the fact that you built a PCB board for this, design and built, and why did you not just then substitute? I mean, that's fine when you're testing, but why did you not just substitute the two diodes for a single diode of equivalent voltage drop?
I did it, but it didn't work.
It didn't work? Oh,
nope.
I don't know about that. Something wrong there. It should have.
I put a higher diode here, just one single diode of 9, no, not 9, but 4.5, I think. And it was still activating here, even when I had low here.
Yeah. Is this a Zener diode here, though? The symbology here? Because that's not really the symbology for Zener diode, is it?
Yeah, actually, this one I have just one small bracket here in one side.
That's not usually the Zener diode symbology, though.
Yeah, usually we have two.
Yeah, I think you got the wrong symbology there. Okay. Yeah, I'd like to, something we could look back in the lab maybe later on there as to why the 2 diodes work and 1 didn't. I guess there's something there to be pursued. All right.
All right.
All right. I guess that's about it time-wise, unless there's somebody else that has a question. Denis, I don't know if you have a question. Or...
No, but Ron is still.
Is he still?
Which type of diode is this?
So which one?
Zener diodes, 2.7 volts Zener diode.
So you use 2.7 volt Zener diodes. Okay. All right. Are we satisfied, Mr. Broad? Mr. Broad is unable to join us.
Yes, I cannot hear him.
No, it's because of this. He is the one that is dealing with the streaming setup, and due to the circumstances, he can't intervene. Okay. He's using all his computer power to enable the streaming. So if he tries to interject via audio, it'll the whole house of cards will come crumbling down. So we chose to just keep him mute, and we said if he had some really serious questions, he could just send it to us through the chat sessions, which he seems to be doing quite well with.
Okay.
All right. Yeah, and he's indicating where time is up anyway. So very good presentation.
Thank you.
Thank you.
Yeah,
and we're somebody's got a fan that just turned on or something.
Oh, that's me. They're drilling down the hall. Sorry.
Okay. All right, so we'll take. The production value is really high on this today. Okay, so we'll take a 12 or 13-minute break. Deal with the paperwork side of this, and we'll return at 2:30 for a presentation from Fernando de Martin digital alarm clock. So he will present his digital alarm clock at 2:30. Fernando de Martin. All right. Thank you. Okay. So one more time, one last presentation for today. We've had a good show so far, a lot of good presentations, a lot of good information, learning all kinds of stuff. So I'm happy to see that. And that's going to probably be the same thing for the remainder of the week, where we've got some great presentations coming up. Today, to finish off our presentation, day one, I guess, we're going to listen to Fernando de Martin talk about his digital alarm clock. So, Fernando, are you ready to go?
Yep, I'm just gonna set up my screen here.
Okay, so anytime you're ready, you can begin. The floor is yours.
Can you guys see my screen?
Yep.
All right, so hello everybody, welcome. My name is Fernando de Martin. I'm a senior student here in the Industrial Controls option in the Electronics Engineering Technology program at NBCC. And I'm going to be talking about my senior project, which is a digital alarm clock. So here's a little preview of what I'm going to be covering in this presentation. I'm going to start with like the concept and idea of the project. Then I'm going to go over the functionality, then the software, then I'll describe the final build. And finally, I'll make a brief comment about testing. And lastly, I'll give a brief conclusion. All right, so when it came to picking the idea for my project, I knew I wanted to do something that was not overly complex, but complex enough that I would be able to sort of explore all this, at least the majority of the skills that we learned in the program so far. So, for instance, I knew it would be something related to programming and like, coding and stuff like that, because truly that was the part of the program that I enjoyed the most. And I still remembered like the first class in term 1 where we had NCRC, computer control devices, with Mr. Standen. I still remember that class as one of my favorite courses in the program, and like something that was really fun. So I knew I wanted to do something similar, which involving, programming and constructing something. So after a little bit of research, I ended up selecting a digital alarm clock as my project. In the formal proposal for the digital alarm clock, I defined a scope, which meaning like the minimum functionality that the project needs to display to be considered a successful project. The scope defined was that the project must keep time using the real-time clock module, must display that time on the LCD screen, must store the date and time values between power cycles, meaning that if I unplug the project, I'm not going to have to configure the clock again. And also the project should allow the user to configure the project directly in the final build with the switches. And also, as it is an alarm clock, a buzzer should be sounded when the alarm time is reached. So here you can see the concept drawing, which shows the key controls and sections that I would need in my project to fulfill what I set up for the scope. So here you can see the block diagram, which shows all the blocks that I would need to, make sure the scope is fulfilled, and the relationship between those blocks. So at the top, you can see the USB module, which is providing the 5 volts required to power the circuit. Those 5 volts power the real-time clock module, which keeps time. The 5 volts are also powering the microcontroller, which is going to read the time. It's going to read the signal from the real-time clock module and display it on the LCD screen. On the lower portion of the diagram, you can also see the user input block, which consists of 3 switches: a menu, a plus, and a minus switch, which I'll detail a little bit more later, and also a buzzer block that consists of the buzzer. So here you can see my schematic, which provides a better description of how the circuit works electronically. In the top left corner in section B2, you can see the USB module J1, which when connected to one USB cable providing external power is going to provide 5 volts and around the 5 volts required to run the circuit and around 5.2 milliamps of current, which is the typical current draw for the ATmega 328. It can rise to up to 9 milliamps depending on what the circuit on the current circuit operation, but typically it's at 5.2 milliamps. In section C2, you can see the real-time clock module, which provides the 2 signals connected to the microcontroller. SCL, which is the clock signal used to synchronize communication between the microcontroller and the RTC, and SDA, which is the data signal where the actual data is being transmitted, where the actual time values are being read by the ATmega. The real-time clock module uses the signal because it's using I2C interface, which I think we've seen before in previous courses. In the center of the schematic, you can see the microcontroller U1, which is an ATmega 328P. You can notice there on the left, there's a 16 megahertz crystal connected there. That's because I'm using an external oscillator instead of the internal 8 megahertz oscillator of the ATmega. Under the microcontroller, there also are the switches S1, S2, and S3, which, as you can see, they all have pull-up resistors as well. To the far left of the schematic is the LCD display, LCD1, which is very similar to the ones we've used before in previous projects and previous classes. But instead of the typical 16 by 2 character size, I'm using 20 by 4. And you can also see that there are headers H2 and H3 between the LCD and the microcontroller. And that's because the LCD is not directly mounted on connected to the microcontroller, but instead connected through a ribbon cable. Also in section C6, you can see buzzer LS1, which is a simple piezoelectric buzzer that is powered straight from the ATmega. So now I'm going to talk a little about the software. And to start, I'm going to showcase here my code, the flowchart of my code. And also, I realized that I think I did not include the flowchart in the documents package I submitted for the instructors. So sorry about that. But also, I did not have the code flowchart ready by Friday. So yeah. Anyway, by looking at the flowchart, we can kind of follow along and understand how the program works. So at system start, 2 things are going to happen. First, the microcontroller is going to read the time from the real-time clock and then display that time on the LCD. Also, there's going to be a check for key presses while the time is being displayed on the LCD. So if the user presses the menu key, the user will go down a menu tree of settings, where they can change the time and date values and also the alarm value. And if the user is in the clock screen and presses the minus key, it presses the minus switch, the alarm would be toggled. But also you may notice that here, the start of the flowchart, there's also a second thing happening at the start, program start, which is the microcontroller reading the alarm time values from its EEPROM memory and saving them in flash memory. I'll detail a bit more about how that works later. And then after that, if both the alarm is set and toggled on, the microcontroller is going to constantly check for the time. So if the current time is equal to the saved alarm time, the buzzer is going to turn on. Excuse me. So here I have a few snippets of my source code. First on the left is a library, is a declaration of libraries, and also the definition of the CPU speed. And as you can see, I'm using 16 megahertz, since I'm using the external oscillator that is 16 megahertz. And to the right, you can see a portion of the main function, where I define inputs and outputs for the switches and for the buzzer, for the LCD pins as well. I initialize a couple of functions like the millis function, global interrupts, and the LCD. I also do the first time reading and read the alarm time from the EEPROM, like I had previously mentioned in the flow chart. And the reason we do that is because the EEPROM has a limited number of write and read cycles. So if I have to constantly read the alarm time from the EEPROM, it's gonna fail pretty soon. So the EEPROM is only read at system start and then assigned to a variable that's in the flash memory. Also, here's my it's the while function, which you can see is reading buttons, getting the time from the RTC and displaying it on the LCD display. And to the right, I have a function used to actually read those time values from the RTC module. So there's first declaration of variables, then I2C functions to initialize I2C communication, and then the variables below that get assigned by the values in the variables below are assigned based on the internal registers of the RTC module. So here we can see a snippet of code source that describes the menu tree. So when the switch is pressed, the menu switch is pressed, it's going to start a count, and that count is going to go up as the user navigates the menu tree. And when the count reaches 7, the values will be saved. And as you can see on the bottom there, first they will be set. The values will be set to the RTC module, and then the time and date values will be set to the RTC module, and then the alarm date for hours and minutes will be saved to the EEPROM to be read in the next system start. So here I have just an example of using a switch, pressing it increasing value, decreasing value, and also in this case it's for hours. So if the value goes up beyond 23, it's going to reset to 0. So the user can just keep going and reset. The values are reset. I'm not going to get 60, 61 minutes. And also below that is the if statement that checks the alarm time, checks the current time for the alarm time. So if they match, the buzzer is going to be turned on. Excuse me. Okay, so now I'm going to talk about the final build. And as you can see here in the photo, I have the final build, displaying time on the picture I took yesterday. In here you can see the enclosure, the LCD display, and the switches on top, and also a USB cable plugged in the back. For this project, although a prototype was developed in the SPL1, for the final build, we developed a PCB board. So here's the final layout for my PCB board. Is a 3-inch by 3-inch single-sided PCB, which took honestly quite a lot of time to design. It's very tricky. I'm sure everyone here who did a PCB is gonna agree with me. And this is version 2.50, which I arrived at after 7 iterations. So yeah, it took a while. And also on the right, you can see the component overlay, which outlines where components, important components, will be located. Okay, so now I have 2 photos of the final build with labels, and I'll actually show in the back. On the top there, you can see the switches. I have 3 linear single pulse, single throw switches. They are push buttons. At first, on my first schematic and my first prototype, I had 5 switches, but I managed to optimize them to just 3 and still get the same functionality. Excuse me. They are mounted just by drilling holes in the enclosure plate and screwing them on with hex nuts. There's also There's also a brief consideration of user design aspects in the placement of the switches, because both in the concept drawing and the prototype, I had the switches aligned horizontally, but at first I called them menu up and down. So after discussing with Mr. Metcalf and also reading up a little on user interface, I realized that probably setting them as minus and plus would be more intuitive for switches that are aligned horizontally. You can also see the LCD display, which is, like I said, is a character display module, 20 characters wide by 4 characters tall. In front of it is a bezel, which is mounted on the bezel is mounted on the enclosure, and the LCD is mounted on the bezel. And there's also a little glass window protection thing on the front. On the photo on the right, you can see the back of the project, which shows the micro USB jack, which is mounted and screwed on the enclosure, and plugged in with an USB cable. I'm not going to show the entire parts list in this presentation, but just as a general idea, the bill of materials for the project came up to around $165. So I'm going to talk a little bit about testing. Usually the testing is done for the senior project. Usually testing is done before the project and presentation, but due to the COVID-19 restrictions and the limited access to lab time we had, those tests were postponed to the next week, and an addendum with the actual tests and results will be submitted on June 4th. But for now, I'm just going to describe the intended tests. So the first one I'm going to do is test for system time accuracy by comparing the project to the online time signal that's available on the website on the website of National Research Council of Canada. I'll synchronize both clocks and then let them run and for a certain amount of hours, and then look for offsets in the time readings. And then I'm also going to test for system time stability, which is where I'm going to measure. We're going to use an oscilloscope to measure clock jitter, which is essentially the difference in the position that the current clock edge of the signal is to that of what it should ideally be. I'm going to present the results of the first test in both a table and a graph, and I'll present the results of the second test in just a graph. So in conclusion, my final project is completed and functional. I designed a PCB, mounted the components on the PCB, mounted the PCB on the enclosure, all the steps that I had planned to take to build the final, to construct the final build of the project have been taken. The scope of the project was covered, like we'll be able to see in the demonstration in a little while. I didn't have excuse me, I didn't have many issues during manufacturing, but one of the issues that I came across was I had a pin failure during soldering on my USB connector, so I had to order another, and that arrived like 2 days before the evaluation, but I got it mounted and it's working. So as far as possible improvements that I could make to the project, a big one is improving the efficiency of the source code, because I written this code mostly based on a project from another person, but who used Arduino. So it was essentially translating the Arduino language to C language, so I could ran the program in a standalone microcontroller. So I do use like a few libraries and maybe a few macros that are not as efficient as they could be, since I'm basing myself off Arduino. So, future iterations of this project should probably consider optimizing their source code. And also in regards to the switches, I used linear switches, which means they don't have feedback, like physical or audible feedback. Like when you press the switch, you're not gonna get the nice click, like that click noise, you're not gonna get it. So for projects like this, I think it's important to get a little bit of physical feedback and audible feedback too for the user. So for future iterations, I'd probably consider using tactile switches, which they have the nice click and bump. So here are my sources, and thank you for watching my presentation. I'll be moving on to the demonstration portion now. Just a minute while I get the second camera up. Just 1 second. Okay. Can you guys see the project?
Yep.
Okay, so now I'm just gonna plug that in. Okay, so not sure how well the screen is gonna come up on. Can you guys read the numbers on the screen?
Yeah, we can read them, yeah.
Okay, so now I'm just gonna go down the menu tree and set an alarm and then wait for the alarm to ring, basically. So just to show you, I'm gonna press the first key here on the top to go down menu tree. It's gonna say time and date setting, and then allow me to change numbers, but I don't want to change the current hour now because it's already correct. So I'm just gonna keep pressing the menu switch until I come up to this screen, which allows me to change alarm time. And I'm gonna make it set it for 2:55. Oops. I mean, we might not have seen this, but I'm pressing the minus and plus switch here to decrease and increase time value. So now the settings are being saved. Values are being saved to the EEPROM.
I think you set it to 155.
Yeah, but it's 155. Oh, sorry.
Yeah.
Thanks for noticing, Mr. Leger.
Yeah, no problem.
We've been here a while.
All of a sudden, tomorrow the alarm goes off during another presentation.
Yeah. Okay, so now 255, and I can press the minus switch here to toggle the alarm on and off, and you can see the little X there. Oops, sorry, the little X there, indicating that the alarm is toggled off. Sorry. So just gonna wait for it to ring now, I guess. I can show you guys the back while we wait. Like, here's the USB connector, just little screws there, cable, switch top. Also on the bottom there's feet, non-skidded dizzy feet. So almost there. And then it makes noise. And I can press the minus switch here on the top to turn it off. And that's it for my demonstration. Just gonna pop back to it.
All right. Thank you, Fernando. That was an interesting presentation. Very good demonstration of your alarm clock there. And we won't have to wait till tomorrow for it to work.
That's good.
Denis, did you have questions you want to start off with? Or?
Share my slides here.
Yeah. Can you bring up the schematic, Fernando?
Yes.
Oh, by the way, it's nice seeing you there. You didn't have your webcam during the presentations.
Oh, really?
Yeah.
Oh, Jesus. Yeah. Oh, sorry about that. That was not my intention.
You were talking about the input current being 5.2 milliamps and 9.5 milliamps, but here you have it labeled as 5 volts, 2 amps from the USB.
Because that's the rating of the connector, though.
Right. Okay. Dennis, we can hear you laugh there.
Oh, jeez. Yeah, sorry.
All right.
I was just laughing at Fernando's reaction to the webcam being on.
Oh.
Yeah, like I didn't know. You guys should have told me. But yeah, sorry about that.
That's all right. Well, Dennis, if you have any questions there, I didn't take much notes while I was doing.
Oh, okay. I've got a.
So I'll have to look.
I have a few.
Okay, go
now
ahead.
that I'm on the hot seat.
Yeah.
Could you? This one actually comes from Mr. Broad, Fernando. Could you elaborate on the terminology sound versus noise? You use the word noise. What's the difference between sound and noise?
Yeah, sorry, I shouldn't have said noise, but because noise is something that is not intended, and the buzzer provides sound, which is not distortion of a signal or anything. It's signal as it is intended to be.
All right, I don't know about whether it's not distortion free or not. I mean, ask anybody who plays the guitar into a distortion pedal. It's wanted, right? I think we just have to. Noise is typically a negative thing that is unwanted, whereas sound is a desired outcome, maybe, right? So noise tends to be more depends, I guess. It tends to be statistically more diverse and interfering, right? So, could you show me your flow chart? I was really intrigued with your flow chart.
Yes. There we are.
Yeah. Okay. So, from the point where it says start, could you just talk to me about what happens at the next step in your program?
So immediately after system start?
Sure.
Well, what happens is the microcontroller reads the time from the RTC to later display it on the LCD screen. And also at system start, the microcontroller reads the alarm times that were set in the EEPROM to the flash.
So those two events happen at the same time?
Yes.
At the same time?
No, not at the same time. You're right. Yeah. The alarm data is I can find it on my main function here, I believe.
Sure.
Yes.
Please, I'd love to see that.
Here. You can see that the time is read first, and then the time from the RTC is read first, and then the alarm time is read from the EEPROM.
Sequentially, right?
Sequentially, yes. Not at the same time. Sequentially.
So let's go back to your pseudocode for a second. So your pseudocode for me doesn't demonstrate that. It demonstrates things happening in parallel threading, okay, which I'm 100% sure that the Mega 328 does not do, okay? It doesn't have multi-threading capabilities, okay? So why did you lay it out in parallel like that?
Honestly, because I use the flowchart more of like a design guide, if you will. So I knew I wanted to do those things relatively close to each other, or at least like right at system start. So I put them there happening at the same time, I suppose, because that's how I designed the code in my mind, I guess.
But in your code, that's not how it's going to happen, right? We're supposed to write our pseudocode and our flowcharts for us to then be able to port over to our code, right? It's a blueprint of what our code is supposed to do. So I can understand saying, well, here I have a chart of just what happens for the time part and just what happens for the alarm part as just a way of laying things out. But then eventually somewhere there has to be an overall code design that says, now I'm combining these things together. So yes, they have to be in some kind of sequential format, barring anything like interrupts or anything like that, which again may or may not be happening in your code, right? So I think that it does make the leap from your design to your code somewhat difficult to follow, if not understand the relationship. All right. I mean, I know, for example, when I do my code and I do a flow chart or pseudocode, I'm putting in my information in whatever sequence I'm looking for. And then when I start my programming, the titles or the blocks are actually the comments, the block comments that I use in my code for a layout, right? Because I'm using it as a tool to develop that, right? I'm going from, for example, from block diagram to schematic, right? Things like that. It's the same concept. So I found this really hard to follow. For example, if you get down to adjust time and alarm settings there, that last process block there, then you're going up again. And you're going here to, well, is it going to get time for RTC? Is it going to get alarm time? Or does it go right down back to sound buzzer? I mean, do you understand where it's hard to follow the flow, right? Okay, so you probably want to look at that again and just revisit that for yourself, right? Could you bring up a picture of your device there where it shows the LCD?
This one?
Sure, sure. So you've got a nice display there. It actually looks really nice in this particular picture here with the contrast and everything. Just a quick question. Even when you demoed it to me, you have a 4 LCD, a 4-row LCD display, which is substantially more money than a 2-row LCD display. But you only ever use 2 rows for it. Can you justify the purchase of that? And if so, what tell me, what was your thought process there?
Well, my thought process there was basically I wanted to use the 20x4 from the start, just to be able to create a more interesting clock display, if you will. But when it came to the coding, like I said, I based myself off that Arduino program. When I finally got that working, I just ended up going with that, which it was reading for 16x2. And I just kept telling myself I was going to fix that later, and I just never fixed it. But yeah.
It's too bad, because I think, I even think that, to be honest, you crippled yourself a little bit by looking at Arduino coding. I think you, having gone through the embedded course and everything, had more enough capabilities to really lay out your own code, design it, and come up with something that would have been just as good, and not be crippled by that, and not probably take advantage of these 4 lines and be able to do something really interesting with that. All right, just by all means, sometimes looking at other people's work is not necessarily an advantage, right? Could you go to your schematic, please? And also, just want a quick comment. Show me your code for a second there. Just a quick comment on your code. No, previous slide there. Very, very difficult to read. All right, the comments are very difficult to read. I don't know if this, I know this works well when you guys are programming. I encourage a white on black type of code when you guys are programming, just to kind of keep the eyes from bugging out after a couple hours. But the reality is, when you're going to be displaying code to people for brief periods of time, contrast is everything, and your comments and that are very, very difficult to follow through. Even that first little block there where you have your includes and defines there, it makes for a little bit of a difficult read, because it's not really a white on black contrast either. Okay, right. So it makes it difficult for that. So you kind of want to be careful of that. Okay. I know I'm the same way. When I do coding, I really like the subdued colors, and I don't want that big white page blaring in my face for 3 hours or whatever. But when you need to show code to people, that's a whole other story. They're only exposed to your code for 30 seconds or a minute, and they just want to be able to read it really quickly. Right? All right, let's go to your schematic. I just wanted to point out, I got a comment on that there. Could you tell me 2 things? Number one, the selection of X1 16 megahertz crystal. Why did you do that? Why not pick one of the internal oscillators for the Atmega 328, or use something else? Why did you decide to go to the 16 megahertz crystal X1?
Well, to be honest, just because the project that I mostly based myself on, they had the 16 megahertz crystal there, so I implemented that as well.
Yeah, that's not a good answer, my friend, though. I mean, you need to just, that's an extra 2 or 3 part count. And okay, what do you think, though? What do you think? Why would you go to that instead of going to the internal oscillator, for example?
To provide a faster speed for the system.
Oh, I don't think you need to be chugging along at 16 megahertz to make an alarm clock, to be honest. What else? What is one of the characteristics of a 16 or whatever megahertz crystal oscillator as opposed to other types of oscillators, let's say? What type of oscillator is internal? Here it's a crystal oscillator. What's the internal oscillator for the 328? Do you remember?
I'm not quite sure, no.
No, you didn't look at you. Well, I know we talked about it in the embedded course, but
Yeah.
it's an RC oscillator, right? So why would the crystal oscillator be better than the RC oscillator?
Like I said, I'm not quite sure because I just used the oscillator based myself on the project.
Yeah, but I'm sure in your 2 years here, you've talked about timekeeping, stability, and so on. Think about it a little bit. An RC oscillator is dependent on the resistor, capacitor combination values, right? What about a crystal oscillator?
Well, it's dependent on inductance, no?
Not inductance, no. What physical parameter? Not electrical necessarily, as opposed to physical.
Vibration?
Yeah, somewhat. That can work against you, but it's based on the lattice structure of the crystal, is it not? Right?
Yeah.
And how it's cut determines how it oscillates. Right? So do you think that the crystal oscillator is what characteristic electrically do you think it would have over the RC? I'm sure you've built all kinds of RC circuits in your 2 years here, and I'm sure you probably noticed that when you did that, one of the characteristics of those oscillators that wasn't so great was what? When we talk about oscillators, what's one important characteristic?
Stability?
Stability. Yeah, definitely stability. So a crystal oscillator is a lot more temperature stable, right, than an RC oscillator ever is. It's just stable, more stable, period. Okay, so if you're using this as a good timekeeping device, you want that stability to be quite high, right? The accuracy to be quite high and repeatable, right?
Yep.
Okay. So, all right. What else did I have here? I noticed that in this schematic here, you're right in pointing out you had H2, H3 headers that will have a ribbon cable in between. Is that the only device that is connectorized in your design?
No, not actually. Yeah, the J1 and the switches are also connected by terminal blocks.
Okay, so that should have been indicated on your PC, on your schematic there too, right? Okay, by all means. Okay, could you go to some of your code for a second? Let's take a look at that. Denny, you don't have any more questions, do you? I'm hogging this time there.
No, go ahead.
Could you hold on here? I'm trying to remember. Yeah, so this was I noticed you used I guess I read it wrong. I guess I noticed you had used switch menu equal to low, and then later on what I thought was switch menu, but it's switch menu count is equal to 1. I was thinking one of them was supposed to be true versus false, but it's not. It's switch menu count, and I misread that, I guess. All right, that's fine. And then you use a series of delays. What's another instead of delays? What's another way you could have done this instead of using delays that might have been less crucial to this timekeeping device, right?
Using interrupts.
Yeah. So what advantage is there to using the interrupt versus the delays?
Well, the delay is gonna stall the entire program while the delay happens, so that might affect timekeeping.
So how does the delay work then? That _delay _MS 2000 there, for example. How does that work in very basic general explanation? When you call that delay, what does it actually do?
It's like a function that's gonna run itself basically for that amount of time. So gonna run delay milliseconds for 2,000 milliseconds, let's say.
And nothing else happens.
And
right?
nothing else, yes.
So how does the interrupt overcome that?
Well, the interrupt actually interrupts the program, and like it's not an actual function like delay MS, so it's not gonna stall the program in that same way.
So if it's not a function, what is that? I'm looking for a key word here. I'm looking for you to describe to me the interrupt process there. How does it trigger, I guess? Again, the difference between an interrupt and a function, right?
Well, the interrupt is basically not checking, but checking for a condition that when it happens, it's gonna interrupt the system.
Is it checking really, or?
Yeah, no, that's not the right terminology. I'm not quite sure.
When you have let's say a timer, let's say you decide to do a timer, instead of delay milliseconds 2,000, you decide to do a 2-second timer, okay? Where does the setup and the actual counting and all that happen in the microprocessor, as opposed to the function here? In the function here, it goes and it loops, right? X number of times, whatever times it takes for 2,000 milliseconds. If you set up a 2-second interrupt, where is the counting being done?
It's being done. I know it's not being done in the same way as the delay function, as like it's counting the program on the same memory, I'd say, but
no, it's not. Yeah, it's not in the same memory, that's for sure. Where is it being done? That's what makes an MCU different from a microprocessor too, and it's one of the it's a built-in. When you set up bits, what are you setting? Bits in what?
In the registers?
Yeah, it's an actual counting register, physical register that you load a certain amount, and then it counts electronically via the clock pulses of the clock circuit, right? And it's left to do its own counting while your program can keep on working. And then what happens when the counter counts to a certain value? What happens? Because
sorry?
No, go ahead.
And when the counter reaches the set value, then the interrupt fires. And
so what do we mean by an interrupt firing? That's right. That's the perfect term. What do we mean? What is the interrupt firing?
Is the microcontroller reading the values in the interrupt register?
No, when the interrupt register, let's say, overflows, that's a very common way of doing it, right? You count till it overflows, right? When it overflows, meaning it goes all ones to 0, and you say that's the time it took, okay? How does the MCU know that it overflowed? What happens so that it doesn't have to look at it all the time, doesn't have to look at the counters all the time? It just waits till what happens?
Well, isn't there an overflow bit that is set when
That's right. An overflow bit. That's right. That changes.
Yeah.
Right? From sets or clears, depending.
Yes.
Okay. And that's what triggers your routine, your interrupt routine, right? That now is a function that does that. So it's a hardware trigger that some event does by itself that you don't have to worry about it, so your program can keep on working and doing things and not have to go check it until that flag flips, right? Whereas in a function, you always have to go back and take a look, right? And in delay MS, you have to look at it to make sure it's done, or you have to wait till the call comes back, right? The returns, right? Okay, so very fundamental differences there by all means. All right, I think I'm way past my questioning time here, so we'll stop there. Thank you. You've got a really nice project there, Fernando. I hope it serves you well for a long time, and I hope you get to maximize the display usage. All right.
Yeah, I'll be sure to do that. Don't worry.
Right on. It'd be a waste for those 2 other rows to be wasted, right?
Absolutely.
All right. Okay. So thank you very, very much, everybody, for participating in this first day as either presenters or observers. Tomorrow we start again at 8:30. Tomorrow morning, please note that the stream URL is different every day. So if you want to observe again tomorrow, you'll have to use the next URL there in the series on the schedule. So every day has a different URL to access it. I believe that once this is done and the recording stops, this stream is still, you can review this stream once again and access it at any time. I'm not sure, Mr. Rod, if that's right away or if there has to be some processing then to engage that. But anyway, I do know that it is accessible after a certain amount of time in the future. So by all means, if you have after processing, okay. So Mr. Broad indicates there has to be some processing time there. So we'll let you know when it's available later. And I'd also like to note that we did have a little bit of problem with that stream this morning. So there might be a few gaps in the time there, and that's unfortunate. And we apologize for that. So again, thank you very much for participating. If you have any feedback, by all means, let us know. We're always eager to hear about the feedback. And we'll see everyone tomorrow morning. Thank you.